get it started. The EML webinar, we have a lot of viewers, both live attendees, and also later on we posted in YouTube channel and Weibo in China. There are a lot of viewers over there. Many of them are actually younger students. Those are in graduate school. And I was reading your website the other day. I noticed that when you were in PhD degree program, you worked with a lot of people. That has been very productive during the PhD time. So do you want to share some of your insight, or, you know, in hindsight, how did you cultivate those collaborations and being so productive? I think that would be beneficial for the other graduate students who are watching or who will be watching this one.
Sure. Well, first of all, good morning, everybody. And thank you, Teng and Zhigang, for inviting me here today. It's really exciting. And it's a pleasure to be able to share some ideas and past stories with all of you guys. It's nice to see you all. Yeah, I mean, the story of my PhD, I think, was unique in many ways, but it was thanks to my two co-advisors that really gave me a lot of freedom. I had one advisor that was a physicist, Professor Vitaly Nesterenko, and actually, interestingly, another physicist, but an experimentalist. The first one was a theoretician. That was Professor Sang-Ho Jin. And the combination of the two really allowed me a variety of experiences and a number of different collaborations. But mostly I had a lot of freedom, which was what made it all possible.
That's great. And so our panelists, if you have other questions, feel free to chip in and we can keep the discussion going. I mean, at the PhD level, so when you work with different collaborators on different projects, I also noticed that your interest, and at least from the publication I can see over there, it's actually quite diverse even at that time. So were there, how did you handle this multiple topics and you know, producing multiple topic papers at that time?
Again, I think a lot of it was fortuitous. At the time, one of my two advisors, Professor Jin, had just moved to UC San Diego from Bell Labs, and his lab was being built, and UCSD did not have a working transmission electron microscope. I was in a material science program, and the microscope there was, when working, was very crowded. And so my advisor said, well, the lab is being set up, so why don't you go and visit my collaborator at UC Berkeley? And so that's when I moved for, I think it was for a year, and then, you know, frequent trips thereafter to UC Berkeley, working with Professor Rob Ricci. And he gave me the opportunity, number one, to learn at the Center for Electron Microscopy, LBNL, up at the Lawrence Berkeley Labs, the opportunity to use different microscopes, which became handy because then I was the microscopist of the group, and the group was very large at the time. And then I also had the opportunity to explore topics that were not directly related to my PhD, but were projects that Professor Ricci asked me to help with. And so they weren't exactly topics that I branched necessarily off into. I wasn't, you know, multitasking myself on different things. I was asked to help. Oh, can you help with these? Or can you go take these measurements? And somehow, you know, eventually in different ways, they came to fruition after a few years. So a lot of it was just luck and opportunity.
I wonder if I might just chime in. Hi, Chiara.
Hey.
Lots happened since I saw you in January. I hope you're doing well.
No, different times.
Hi, everyone. I just wanted to continue that vein of questions, because Chiara, one thing that's very interesting as someone who was in your group very early on at Caltech is seeing how your research has evolved since then. I mean, a lot of, nonlinear waves and so forth, and there's still that component, but there's so much additional sort of topics. I wonder if you could just comment for all of us about how you choose problems. Are you guided sort of by intuition and just sort of what's interesting? Is there a thread you see in your own past work that has sort of guided you in that? Or is it sort of targets of opportunity as you see what you know and what new problems arise? Does that make sense?
Yeah, it does. I think it's a bit of a mix. There is for sure that thread, and I think the thread of these architected materials came from really my PhD that was working on different kinds, but still architected materials, where instead of 3D printing, at the time we didn't have 3D printers, we were assembling these ball bearings of different shapes and forms. But to me, the ball bearing was a unit cell, right? So somehow that theme kind of continued on, and in a way it's what I consider academically home, right? It's a very comfortable space, and maybe that's why I choose to talk about it most often than not. At the same time, there are other situations that I think also from the style of my PhD repeat themselves, like this idea of having opportunities. For example, students, like you, Jordan, that come with ideas and brilliant new concepts and suggest things like, oh, we should try this. And if they make sense, then why not trying, right? And sometimes these directions have led to things that were not in my initial mental spectrum, right? And I'm thinking of projects related, for example, to these all ionic temperature sensors, which is a direction that the group picked up maybe 5 years ago, thanks to a really creative postdoc in Di Giacomo, which really kind of enabled it, right? I think there is a combination of opportunity. There's a combination of, say, collaborations. When somebody says, hey, do you want to be on this proposal, right? And all of a sudden you're opening new directions that you weren't necessarily focusing on in that moment. And of course, there is your own ideas, which stem from your kind of career of research that developed. So there is a little bit of that. The downside of that is that the group becomes bigger and bigger as the years go by.
That's great. Thank you for sharing. And actually, I remember in a very early stage of EML webinar, one of the speaker, I believe it's Xuan He, shared with us that actually some high school student probably from California emailed him that, okay, really enjoyed his EML webinar. So this is one of the evidence that how wide is the viewer base of EML webinar. And I'm gonna shoot another question. Basically, it's asking this question, hopefully on behalf of those even younger generations who are undergraduate students. So if you can time travel back to your college time, do you have any advice to yourself at that time, after this many years now as a professor at Caltech doing all this exciting research?
Wow, that travels back a little bit. So just to start, my college years have been spent in Italy. So in a really, I mean, at the time was a really small community college, really, and which was serving the local industry around my hometown called Ancona. It's probably a small place in Italy you haven't heard of before. Now, there, how do you go from there to Caltech, right? And I think, again, was the concept of looking out for opportunities and pursuing the ones that are offered to you, right? I think for me, the way I went from Italy to the US, which was not something was on my spectrum at all, I wasn't ever planning to do that, was that when I had to do a senior thesis there, and my advisor, my senior thesis advisor said, oh, there is a friend of mine in the US, they need some help. Why don't you go for a few months and finish this thesis there? And I said, okay, where in the US? And they said, San Diego. I'm like, oh, great, this is even better. So of course I'm going to California. And that's how I arrived in San Diego. And then, so it was really, in a way, an opportunity that wasn't something I was desperately seeking. It just came my way, right? And so there, is the question of, do you take these opportunities? Do you, how much do you want to consider pursuing what you have already in your mind? I wanted to be a Lego engineer. And, and how much do you just take the opportunities that are given and see where you go? And I think I chose to pursue them, but I wonder, looking back, how many others did I miss when I was kind of moving along in my studying years? And I think at the end, my suggestion, which is the same suggestion I give students when they come now in the office and ask, oh, what should I do? Should I do this? Should I do that? I think it's ultimately what feels right to you at that moment, right? If you feel like you need to take this internship because you're excited about it, you're passionate about the topic, or you want to move in that town, then yeah, go for it. Don't think too much about it. And I think that's a lot of how my own career has evolved from the student time to the faculty time.
Do we have other questions from or something that our panelists would like to share or ask? Chiara, Nick?
Sure. Hey, Chiara. So yeah, thank you very much for sharing your personal experience. Here is a question from my daughter. I mean, she, she's curious about many things, including, for example, Lego. Yeah, one question that she asked me about is how do you compare, for example, education in US and Europe? Yeah, since you have experience on both sides of the world, maybe I could relay her question to you.
Well, I think, like, again, my memories of being an undergraduate in Italy are now a little dated. So I would say maybe things have evolved in the last couple of decades or so. However, I think the resources there are not the same as the resources here. I remember, I think I studied mechanical engineering there and focused on metallurgy at the time. And I think I went to the lab maybe twice in 5 years of undergraduate studies. The labs are just not something that are common. They're not available. Everything is studied on a book, right? So I think I had a really strong fundamentals in math, for example, that was something we were hammered on from the very, very early on. I think I was comfortable with the theoretical parts. At the time, the university, I told you it was a small university. I think there were 7 computers for 800 students. So, which only a few, I think a couple were connected to the internet. And I remember the day I could type CNN.com and I was so excited that I could connect somewhere outside. So they were different times, but I think the concept remained that I think here the studies are much more practical. They're much more pragmatic. They're problem solving oriented. In that sense, I think people are much more prepared to face scientific challenges. Because I think in Italy, you study theorems, right? And you're there. And sure, if you want to do applied math, that works. But, the moment, for example, I arrived in San Diego and somebody said, oh, here is the lab. I didn't even know how to switch on the light. It was like, wow, a lab. What do I do here? And I feel like in that sense, here it's more complete because you're trying to get to this multifaceted education where you try to cover the theory and so the analysis, the numerical and so on in a more holistic way. At the same time, here students are much more cuddled, as in a way, and maybe rightfully so, the university is really focused on the well-being of students, on their learning. I think in my own experience in the undergrad, it was really more of a sink or swim approach, as in, you're there, somebody cares, I don't know, you're kind of trying to navigate things on your own. And I think that made me more independent, throughout, I think, my academic career thereafter. I think I could go back and say, oh, wow, I had to face this should be okay, right? So I feel like it's a different type of education, for sure cheaper in Europe. I think tuition for us was like maybe $500 a year or something. So it was a lot more affordable.
Great. We have a Jimmy and also Glaucio here joining our panel.
Hi, Chiara.
Hey,
It's
nice
good
to
to see you again.
Yes, indeed.
Let me follow up on Nick's question, because when his daughter was born, if it's the same daughter, actually,
Yeah.
I'm watching.
Oh, I see. Okay.
What about the K to 12 education between US and, for example, Italy? So maybe the question should be, are US students better prepared when they enter college, or maybe the European students better prepared when they enter college?
So I can't comment because I have not really lived yet the K to 12 experience in the US. I'm now, my kids are in, I just finished 4th and 2nd grade at home. So I think I can only speak to the 4th grade level of you know, style and preparedness. I would say my bases were very strong. I came from a rural community where there were only 9 school children in my class, and only 2 girls. And we had a lot of personal attention. We had an amazing teacher, which I think actually K to 5th was phenomenally well equipped to bring us through and prepare us for the next step. Believe it or not, you know, I have fond memories of all the things I learned, even scientifically, in elementary school, which served me well. You know, the rest, I feel like the public school system where I went were quite large schools that served a very broad community. And I think, you know, I cannot speak of comparisons because I haven't seen middle school and high school in the US, but my impression again is that perhaps the basics of mathematics are a little stronger in what I've seen. So coming out of high school, in my case, I think I had covered what we would do in a freshman year in college, even at Caltech. So you know, that is to say, though, that high school is 1 year longer. So instead of having 4 years of high school, we had 5 years of high school. So maybe it washes out, you know, at the end of the day, that you know, if you compare exactly the number of years of education, it's not too different.
Great. We have Jennifer joining us in the panel. Hi, Jennifer.
How are you?
Hello,
Oh my goodness. Hi,
Thank you for joining us.
I am sorry, Teng invited me to join the panel, but I wasn't sure if I was going to be able to get on very early, so I didn't respond. But it's so good to see you, and of course everyone else, including Jordan,
Jennifer.
John, my colleague.
Hi, Jennifer.
Nick, of course, and
how are you?
Jimmy, of course, my former colleague at Illinois. Wonderful, wonderful.
Jimmy, do you have a question you want to ask?
Yeah.
Chiara?
Chiara, so since you have some successful career, do you have any suggestions for like early career scholars, like postdoc level or assistant level professors? And specific interesting how to choose between research diversity and focus. People always ask a question for young researchers, say, how you vision yourself within 10 years, how you develop your own like research career.
Well, I mean, I don't know if I can really dispense words of wisdom. I feel like everyone's career in academia is so different, and it can be, you know, extremely successful in many different ways. So I don't know if I have a recipe really to share. I can tell you what worked for me. And in a way, it connects with the discussion we've had before about how do you choose research topics, right? And I have to say, as an assistant professor, I was quite conservative, as in I chose to follow, you know, that path of the metamaterials. In that case, at the time, it was more nonlinear architected materials, which I knew was something I felt very comfortable with in terms of my background and understanding of the literature and so on. And I think until the end of my tenure track, I was quite careful not to depart too far from those, you know, strong bases, because I was following advice of senior colleagues saying, you know, choose one topic and make sure you have built a body of work that's recognizable. And second is just because I felt like it was the best way to train students on something I was comfortable sharing. I knew a lot about, and I could certainly, help them navigate the initial years of graduate school or so on. I was also very lucky to have fantastic postdocs. So, it's not just about what I knew, but it was about what the people that were part of the group early on, like Jordan, but also at the postdoctoral level, really contributed dramatically to that, startup, initial step and training of the students. So it was a combination of good choices in hiring, and of course, good luck in getting the students that were phenomenally good, and also try to stay focused. I think the diversification of topics for me started really after tenure.
That's great, and thank you for sharing. And what a panel! Without any coordination, we managed to work as a team to quiz Chiara on her opinion and suggest and advice on from K-12 to undergraduate student to graduate student to postdoc, and we have the after seminar time to quiz her more on other topics. So, Jimmy, would you like to share your slide?
Sure.
The co-editor-in-chief, Professor Jimmy Xia, has an announcement to make before the EML webinar today. Then after that, I'll introduce the speaker. And Jimmy, go ahead.
Do you all see that?
Yes.
Click this maybe. I don't know if, is it okay this way?
Now it's actually partially showed.
How about this?
Yeah, this is also zoomed in. Maybe you just go back to the PowerPoint without the print. Yeah, this is good enough.
That's good enough. Okay. Thank you all very much. And the announcement I want to make is the impact factor just came out on Monday, and extreme mechanics letters got a new impact factor of 4.806. Last year, 2018's impact factor was 4.075. So we're on the right trajectory and doing reasonably well. So again, I want to thank all the authors for submitting your paper, great research results to extreme mechanics letters, and want to thank the editorial team. We have a very strong team. John Rogers from Northwestern, Zhigang Suo from Harvard, Kadia Betaldi from Harvard, Hanqing Jiang from Arizona State, Teng Li from University of Maryland, Matin City from Max Planck, and Sulin Zhang from Penn State. We also have the publisher, Elsevier publisher, Rebecca Kabun. I should also mention that today's speaker, webinar speaker, Chiara, is an editor emeritus. So thank you all for this. And this is a very flat editorial structure. So any author can submit the paper to EML and choose any of the editors, any of the 8 editors as the editor handling your manuscript. And the last thing I want to say is we are certainly very happy about this impact factor, but we have a long way to go. Let's work together to build a very strong mechanics journal. With that, let me turn it back to Teng.
Thank you, Jimmy, for sharing this extremely exciting news about EML. Chiara, I guess it's time for you to share your slide. I'll start the introduction of our speaker today, and go from there. Great. Hello, everyone. Welcome to EML Webinar. And my name is Teng Li from University of Maryland in the United States. I'll serve as the discussion leader today. EML Webinar broadcast live every Wednesday, 10 a.m. US Eastern Time. Now, it's my great pleasure to introduce today's speaker, Professor Chiara Daraio, who is currently a professor in mechanical engineering and applied physics at Caltech. Her research focuses on developing new materials with advanced mechanical and sensing properties for applications in robotics, medical devices, and vibration absorption. She received her bachelor degree from Marchi Politecnica University in Italy, and her master and PhD degree from University of California, San Diego. Right upon receiving her PhD in 2006, she joined the faculty of Caltech and was promoted to full professor in 2010. From 2013 to 2016, she joined the ETH Zurich with the chair in mechanics and materials. She has a long list of recognitions and honors, which includes PK's award from President Obama, elected as a Sloan Research Fellow, U.S. ONR Young Investigator, U.S. NSF Career Award. In particular, in 2010, she was selected by the Popular Science magazine among the Brilliant 10. And I was reading the Brilliant 10 news post published in 2010 last night, and they called her the sound magician, referring to her research at that time that created bullets using sound waves. And now 10 years later, now in 2020, today, the sound magician will talk about the mechanics of robotic matters. Without further ado, here is Professor Chiara Daraio.
Wow, thank you, Teng, for the really kind introduction, and Zhigang for inviting me to this EML seminar series. It's great to hear EML is doing so well. I miss everybody in the editorial board very much, and thank you everybody for connecting and listening to my seminar today. So, mechanics of robotic matter is a topic that my group has been working on in the last couple of years. And let me just start with some introductions and some references to earlier EML seminars that we've heard in the past couple of weeks. As you know, in 3D printing, a lot has been evolving, a lot has been happening, and 3D printing has really percolated slowly throughout many aspects of our life. From wearable devices, you see, for example, here, designer shoes that are completely 3D printed, not just the sole or insole, but the entire shoe is 3D printed. Metal 3D printed has enabled even motorcycle, or in the medical fields, there's a lot of expectations arising, for example, for prosthetics and wearable medical support or medical systems. So really 3D printed has been enabling a lot of innovations in technology and manufacturing. So as we have heard, for example, in talks earlier on, in the EML seminar series, structured materials are in a way a result of this wide availability of 3D printing and 3D printing different materials from polymeric and hydrogel systems all the way to metal and composite materials. And if you think about how materials really derive their own properties, we're used to understanding materials and their properties from the fundamental atomic and crystalline structure that depends on the fundamental composition of the elements, characteristics, for example, of solids, while structures, as we know them from civil engineering approaches, really arise and acquire properties from the geometrical distribution of elements like beams and trusses and bars, right, which are arranged in specific geometrical configurations. And 3D printing, in a way, has blurred, right, this boundary between what we call abstraction and what we call a material by introducing or allowing us to think about structured materials that are also called architectured materials or metamaterials, which somehow break down this concept of materials as we know them. So we usually, especially as mechanicians, we think of a materials as a block of continuum that have properties that are averaged over the volume, for example, density or a certain global stiffness that responds elastically to certain loads. But we think of them as in a homogenization sense. And then structured materials are kind of breaking down this intuition by saying, well, I can really, instead of looking at the composite or the constitutive element, like the crystalline structure, I can look at the mesoscale, right? And I can use computers, for example, to design this architecture and design the properties, again, by selecting building blocks and homogenizing through the volume. And I think Professor Fleck, for example, gave a wonderful review of those methods in an earlier EML seminar. So once we have this design, a common practice in the metamaterials or structured materials field is to say, well, we designed one building block and now I can tessellate it in a periodic domain to create what we call the metamaterial or an architected structure, which may have phenomenally new properties from, extreme, for example, lightweight and stiffness to negative Poisson's ratio to localized buckling and so on. So the 3D printing, though, allows us also to expand these when you think of materials that are non-periodic. And so this was earlier work that I've done in collaboration with Disney and computer graphics colleagues at ETH Zurich, in which the idea of building blocks was used to tessellate objects that have a complex shapes, but also added functionalities. So in this case, you can use this idea of architectured materials in selected locations to add functionalities to the same starting material. So you can start from the same polymer. This is, for example, an armadillo that was 3D printed, or I should say laser sintered, from a polymeric base structures. And you can see that depending on the choice of architecture in different areas, you can have either a hardened, stiff shell or articulated joints without having the need to, for example, assemble it so that joints and other flexible components would require either multiple parts or different kinds of starting material points. So you're expanding with this approach, you're expanding the possibilities and the functionalities of a single starting materials, which enables a lot of applications beyond just the design of toys, as I'm going to show you in a moment. There's another thing that I think everybody is very familiar with, but it's something where I think the rest of the seminar is going to hinge on, is that we know that materials respond to external stimuli. So we're all familiar with the fact, even from household examples like the shrinky dinks, that's something my kids love to play with, is that materials can deform in response to different external solicitations. That can be temperature, like in the case of the shrinky dink you see in these in this snippet that I got from a really old shrinky dink commercial, where you start from a polymeric flat design, which then curls and deforms and shrinks when placed in an oven. But materials can also respond similarly to, for example, exposure to light, to water, variations of pH, magnetic field, electric field, salinity, and so on and so forth. In fact, our chemistry colleagues and chemical engineers have developing a palette, a selection of different materials, both composite materials as well as polymeric structure hydrogels that have more and more of these characteristics. So they are able to deform somewhat controllably with different stimuli. So what is this idea of robotic matter? Well, for once, we should think about first what we as engineers understand as a robot. And in general, if you look at the definition of robot, we're thinking of machines that are able to perform a series complex actions, right? So you think of a robot, of something that has a time controllability, that in time can perform, and that's the concept of a series of actions, and a certain level of complexity, right? So for example, it could be either a grabbing motion or locomotion or so on. So one of the questions that I've been thinking about in the last few years is a question of what happens when we look at structured materials like the one I just introduced and embed in selected location of the volume, right? Imagine the armadillo I was showing before. We embed responsive materials that selectively actuate, deform, shrink, bend in response to different external stimuli, temperature, presence of water, salinity, and so on. So if we do that, the question is, can the material be the machine? So what I mean for that is, can we embed time control? Can we embed logic? Can we embed locomotion without the need for external power supplies, battery packs, sensors? You want all of those components to be in the constitutive property of the architected material itself. So you want to get rid of, when you think of soft robots, you want to get rid of the rigid battery pack or the tether that limits the motion of a soft robot. But you want to have the armadillo, you know, that I showed you before, be able, for example, to grab things by itself or move by itself. So the rest of the talk is going to be focused on three different elements that I think are very important for the realization of robotic matter, or materials that can act as robots or machines. And in general, I'll give examples of each one of them from my own research, but they're by no means conclusive. I think they're just scratching the surface of the potential and the opportunities that mechanics, materials, and in a way, chemistry can enable. So let me start from the first part, which I think it's an important element, and it's an element that we need to be paying more attention to, which is a question of design. If you think of having already structured materials, we've been pretty good in terms of inverse optimization to select a certain property. Let's say, in the mechanic sense, we could say, well, I need a geometry or an architecture that has a certain Poisson's ratio and a certain Young's modulus. You can choose density, strength, you can choose wave speed, you can choose different properties. I just gave you two as an example, and say, well, if I use this idea of unit cell design, and then I homogenize over a periodic domain, I can use, for example, well-known topology optimization methods to determine what is the ideal geometry that would give me the properties I need. So that's something we know. However, doing this process even many times, so iterating over this optimization, in this work done a little bit earlier, we were able to cover to create a database of geometry. Each dot here represents, you know, one geometry with specific Poisson's ratio, and in this case, Young's modulus normalized by the Young's modulus of the constitutive material. But it doesn't cover a very large space. As you can see, a lot of this geometry is clustered around certain values, and it's a bit hard to explore extremes. Sure, we can try to optimize for extreme and find ad hoc designs that can get there. But a lot of it was if you look at, or I would say, if you use many of the conventional optimization methods, we tend to fall often in local minima of designs and not really be able to explore wider research directions or property spaces. So one of the things that we're exploring now is to say, rather than doing single ad hoc simulation, is can we create a closed loop virtual laboratory that autonomously and continuously is able to create or generate geometries that are not necessarily periodic, like the one I'm showing here in 2D, and evaluates them, creating continuously a larger and larger and ever-growing database of building blocks that serve as these architectured elements that allow us to then have larger and larger property spaces in the mechanics sense. So this is work that's unpublished, and credit goes to a postdoc that's currently in my group, Dr. K or Chris Liu, which had the idea to design this generator part of the closed loop virtual lab for materials design based on materials that can grow by themselves. And the idea was really inspired by the way nature and DNA itself encodes information for growth of biological systems. And he realized, looking at a lot of the geometries, for example, of the architectured materials that are well known, like the Kelvin lattice or the octet lattice and so on, that are ubiquitous in the structured materials community, by saying, well, a lot of the building blocks are common, right? There are beams, there are connections, there are bends, for example, and crossbars. And so if we provide to a computer the rules for growth by saying, for example, that a certain bend element or bent beam can connect with a straight beam in certain geometry, then the material can grow itself. So this is an example of what he meant. You can use different building blocks like these T-shaped connections or elbow, straight, or crosses, and you could provide these rules of how they need to be compatible with each other. So for example, the black has to always connect to an adjacent black. And you can provide availability of blocks. So how many bent sections are available for growth, right? How many straight connectors are in percentage available to a materials. And then you can let the material propagate a little bit like a cellular automata that can effectively, just following this rule, create several thousands different realizations of geometries, patterns, and textures that then we can either 3D print or evaluate in this generative loop that I was showing before, using conventional methods well known to mechanicians like finite element, right? And so in that way, we can basically have this virtual lab that starts designing and storing ever-growing, larger and larger databases of building blocks that defy, in a way, the common intuitions, but allow us to explore a larger parameter space. They also allow us to understand the fundamental rules of mechanics, right? To say, how do I design, for example, for higher Young's moduli or lower negative values of Poisson's ratio? And varying the availability of the different building blocks, for example, how many elbow connections, how many crossbars, or how many T-shaped connections you give the computer for generation, you see that you can bias basically this growth towards properties you want. So it's not just a black box optimization, but it's an educated basically growth of materials towards the properties that we need, for example, for specific deformations or properties desired. And I give you examples earlier on in 2D, but what Chris is doing now is to expand this idea for designs of three-dimensional objects and three-dimensional building blocks that have a relatively complex architecture, but intriguing mechanical and deformation properties. So that is to say, we need to think out of the box in terms of having new design tools that are available to us to generate deformation patterns that are interesting for applications that, for example, will evolve, as I'll show you in a moment, towards robotic matter. The second thing that I think it's important to embed is to think about time-dependent response. And what do I mean with that? So as we said before, robots, right, need to perform a series of complex actions in time, which means you need to have some kind of clock or an internal way to control what actuates when. And materials that actuates in very complex and beautiful shapes have been pursued, in fact, for decades, if not centuries. From if you look at the art of shape morphing and shape changing materials, and this slide is just selecting a few examples, which are no means comprehensive, of ways in which in the literature people have described different ways, for example, to start from a flat sheet to a complex shape that is generated in response to external stimuli. The external stimuli could be boundary actuations, it could be manual bending and folding, it could be shape memory effects, like in some of these 3D printed objects and polymer, or it could be due to swelling, like in the case of hydrogels, or even liquid crystal elastomers. And so there is a wealth of ways to design with different constitutive materials to respond to different external stimuli, right? Temperature, water, load, and so on. But most of these examples, albeit they're able to create beautiful, complex shapes, they tend to actuate in one go. So they don't embed the time response in their actuation landscape. So one thing that we started doing, this is in collaboration with the group of Professor Bernd Bickel in Austria, was the question of, if we think of shape morphing structure, can we embed temporal programming in the constitutive response of the material or the architected materials? These can be done in two ways. You can try to print these materials with different constitutive elements, or as I'm gonna show you, you can try to think of mechanics as a mean to control the temporal evolution of these surfaces. So let's say that we want to do a simple example first and design a target surface, which is a lotus leaf, but notice that in this case, the lotus leaf has interpenetrating or interwoven petals. This is something that's not easily done with the conventional global actuation because of contacts, because if they're not triggered at different time, like you see this actuation landscape is depicting. So if, for example, this petal and this petal would actuate at the same time, they would collide and would never be able to close completely around. So we said, can we embed actuation time landscapes whereby some parts of this flower are going to be actuated first and others are actuated later? And I'll give out away already the answer. You can see the top part here, it's a simulation, so it's a discrete model that's used to describe the characteristic of each individual building blocks. And this is the experiment. And you can see that indeed, we were able to encode this information in the deformation pattern and show that in time, it is possible to control actuation of one petal and then the second and the third. So how did we do that? Rather than using the conventional design via homogenization, in this case would not be sufficient because you really do need to have a spatial variations and different properties in different areas. We basically fabricated a flat shell which has a tessellation of unit cells that are all different. And the fundamental building blocks of this unit cell that you see here, for example, in white, are reported in green on the central part of the slide. They have really three fundamental elements that are essential to the design. A base, which functions as a fundamental structural support element. A bracket, which controls the time actuation, and bumpers, which through contact control the geometry of the final shape, or if you want, the curvature of the morphed structure. You can see that the bracket have this H, which is a thickness, which is going to be the temporal control. So how do we do things? Well, once we have these designs of these three elements, we can control the morphing time by varying the thickness H of this bracket. You can imagine that if, for example, temperature was your trigger, simply by diffusion processes, the temperature or the time of actuation through temperature of thicker brackets, it's expected to be slower than the time it takes to actuate very thin and easy to bend brackets. And the curvature formation, the global curvature, comes from the assembly of this local bumper, which control basically the contact mechanics at certain points. So again, how do you design for complex shapes? Well, in this case, we We borrowed from computer graphics again and looked at conformal mapping as an approach for design, in which we determined a certain target surface. We use an isotropic triangulation, much like what you use in finite element for creating discrete components in an actuated stencil. We flattened it, just like you do in a world map, if you want, from a 3D object to 2D. And then we defined bases and bumpers, so the location of these springs and structural elements as the center of this triangulated point. Once you follow the conformal flattening, you can relocate the bases and bumpers to create basically these bracket arrangements that gives us the flattened sheet of architected materials. So one thing that's missing here is the actuation landscape. Now we know what we want to move first, and so we can change the thickness of this bracket based on when we want the actuation to occur. And that gives us basically the full design. But how do we know, how fast and how strong these brackets are? Well, again, we went for a data-driven campaign where the students involved in this project were effectively measuring large number of specimens with different geometry, bracket thickness, bracket lengths, different load applied, and so on, in a bath of fixed temperature. And by collecting this data and storing basically a lot of these displacement time curves of deformation at different applied loads, we could construct a data-driven model, so basically fit the experimental data to a numerical model that then was able to be fed into a simulation framework. Now, the simulation framework is a discrete simulation framework which combined a finite element approach for the membrane with localized springs, for example, longitudinal springs and shear resisting springs for controlling basically the deformation motion of the brackets. And in this discrete simulation framework, we could look at the energy, potential energy of each one of these springs, the compressive springs, the shear springs, the membrane springs, and feed into them the data-driven models that were derived from experiments, and effectively determine the deformation patterns that then would guide the overall simulations to determine the time-dependent response. And so I'll give you some examples of what came out. This is another petal structure in which the petals are all interpenetrating one another. And you can see that this was the target configuration. In the top, you see the simulations, and the bottom is the experiments. These are done in water at about 60 degrees. So they are, we are using a 3D printer. This is the Connex 500 printers from Stratasys. And you can see that each one of these elements contains the bracket, and that indeed we were able to fabricate the shape we initially wanted. But the lotus leaf was something that was shown before. So we asked ourselves, well, can we make more complex shape? And for example, can we have ribbons that self-knot? In this case, we called it a self-interweaving shape, which is a lot more complex because the time of actuation really needs to be spot on in order to avoid collisions in the knotting. And you can see that once again, here's the simulations, and below you see the experiments. You can see that the three ribbons are actuated in different places at different times, and we were indeed able to show interwoven architectures. So this is still not, I would say, it's a time-dependent actuation, but it's still not complex action. I think in this case, we still, although we have shown the ability to embed a time-dependent response on an architected material, which responds in this case to temperature stimuli, it's still not a robot the way we think of it. It's still just a shape morphing sheet. So the question is, can we make it even more complex? So can we embed this complex action that would make us think of a material as a machine? And so the first attempt to doing this again went to shape memory polymers, and uses a lot of ideas similar to the ones that I showed you before. But in this case, we were aiming at obtain propulsion. So we wanted something that would move, that would locomote somewhere. So for motion, shape morphing is not maybe enough. So we wanted something that would amplify strain. And so we had to look at building blocks or springs that had the ability to amplify deformations rapidly. And the attention came to bistable mechanism, and Katya in another earlier EML seminar spoke extensively about the advantages and the beauty of bistable nonlinearity. So I won't dwell too long on that. But the idea is the following. Imagine you have a mechanism like the one you see on this slide, which has two stable positions. One, it's the one you see, and the one, it's going to be the symmetric one snapped on the other side. The potential energy landscape is going to look like this, right? So you can go from A to B basically with a small energy input. And then there is a release of energy in this case, which is going to be larger than the first step, which allows the snap through mechanism. So we added to this bistable mechanism a shape polymer actuator, like the brackets you've seen in the prior example I showed. And then to this unit cell, we attached three elements. In this case, it's kind of exploded view for convenience, but this element is 3D printed in one go without assembly. So you see the bistable element here, you see the shape memory brackets here, and then we're adding paddles here in the front and floating elements for buoyancy. And so this is the unit cell once built. You can see it in a bath of water, it's floating, and you can see that as we keep the water at a relatively cold temperature, the element is in A configuration. As the temperature is increased, we're effectively using temperature to provide this hump potential energy. And then finally, it triggers the bistable mechanism, which is effectively a swimming motion of the paddles in the front. And you see the little floater propelling forward. We can then reload by using a different actuating spring. If you pay attention here, there's a white one and a black one, which has a different actuation temperature and will reload the mechanism to the starting position. So how do we control in time the responses? Once again, is by using these brackets that change thickness. And you can see here, oh, the movie just stopped, let me see. You can see here that as you immerse in the bath of constant temperature water, the elements are supposed, the movie is gonna play again. The brackets are going to trigger at different times. Oh, this is not collaborating with me. Well, oh, wait. Let's see if I can play it here. Yes. You can see that the spring and the brackets are actuated at different times, although the temperature is always constant. And that's because in the on the left-hand side, the thickness is larger. Sorry, it's smaller than the one on the right-hand side, and so you have more time to actuate deformations. So when we do that, we can then create plots of actuator thickness as a function of time to trigger. That's effectively what we extracted from the movie I just showed, as well as the recovery force that we can measure experimentally or through finite element simulations, and hence see how much force each one of these brackets or springs can apply in order to load and reload the mechanism. Now, once you have these building blocks, you can, of course, tile them into arrays and create swimmers that have, for example, multiple paddles. And in this movie, you should be able to see, for example, the actuation of two paddles that are triggered at different times. So you're going to see first the back paddles pushing the swimmer forward, and then the second paddle. And you can add as many as you like to create basically a swimming millipede. or you could create defects like the ones you see on this image, in which some missing paddles would cause the swimmer to, for example, first go forward and then veer or steer up or zigzag around certain objects. We also wanted to show complex functionality to say, well, what if I can do more than just go forward? And so we wanted to design a swimmer that can do three things. It can start from a parking position, swim to a target position, and then release a cargo, like a sensor. In this case, it's just a Caltech, little Caltech penny-sized logo, and then go back to its initial parking position. So what you're gonna see here is, in fact, that there is two springs. One is gonna trigger the motion forward, then the cargo will be deployed. And then, okay, this is a bit of a real-time slow motion movie, so I'll jump forward. You will see the second spring trigger that will allow the swimmer to go back into its parking position. So we thought, okay, this is a first example of a piece of material that's 3D printed in one go, no assembly, no batteries, no nothing, that can do a series of complex actions. Is this a robot? Well, you know, you're still kind of stuck to the fact that because they're shape memory polymers, they can only perform their functions once. So although we can add springs to make it go back and forth, you know, once all the springs have been triggered, the motion ends. And so we went on and said, well, what can we do to make it more realistically looking like a repeatable motion? And here, the group of Jennifer Lewis at Harvard really came to the rescue. Their ability to 3D print liquid crystal elastomers was key in creating materials that can repeatedly and reproducibly perform actions without the need for reloading, for example, the mechanisms. And this is the way they have envisioned doing that. So in Jennifer's lab, they're able to 3D print different kinds of liquid crystal elastomers. Some, for example, that respond to higher temperature, and some that responds to lower temperature. And they can also 3D print passive materials like these structural flaps that you see seemingly attached to the liquid crystal hinge that you see, which allows for a rigid structural element to be added to the system. So in this case, the way Arda, actually, which is a student in Jennifer lab, worked in collaboration with Connor, a student in my lab, is that they envisioned the design of these hinges by changing basically the alignment of the polydomain inks of the LCEs to either trigger mountain fold deformations or valley folds. So you can start from a flat strip and see that, you know, one fold, the valley fold, is going to fold on the left, and the other will fold on the right, being able to control deformations in different directions once a certain force, once a certain temperature stimulus is applied. So these LCEs hinges also can exert forces, and we measure that a bit like a weightlifter, straightening the hinge and letting the hinge lift different weights for a large number of cycles. And you can see, for example, the torque applied as a function of the bending angle in these measured values. And then, and here is the key, is the question of adding this architectured material that I was mentioning at the beginning with local stimuli responsive materials. And here you look at the architecture as follows. You can see that there is 3 different materials in this flat sheet. There is the gray part that you see also here, which represents the passive structural element. That's the rigid polymer that's printed and does not respond to external stimuli. Then you see these blue and orange areas that you see here and here, which are liquid crystal elastomer hinges that respond to different temperatures. And you can see that we use one for the side branch and for the side lobes, and the other for the middle part. So when this sheet is cold at room temperature on a table, it remains flat. But when the temperature is increased, it rolls up a bit like a roly-poly and morphs into a different shape. But let's see it all together. So what you're looking at now, it's a side view of this polymeric sheet. And this is a hot plate onto which the sheet is it's going to be deposited. So I'm going to play the movie and you're going to see what happens. This is slightly sped up. I think it's 4 times. So you see that first the orange, first the blue LCEs respond and curl up into the roly-poly. And then slowly and steadily, the orange LCE or these other linkages here are actuated so that this object keeps rolling. Now, why does the object keep rolling is that there is a clever mechanism in this case that you have a hot surface here, but the air up here is at room temperature. So although you can see these little flappers that look like little legs are actuated, once these little legs reach the top, they cool and hence they fold back. And this enables this rotation or continuous motions that will perpetuate as long as this differential temperature between the hot plate and the room above is maintained. So in a way, you have a polymer that can move itself to different locations. So what are the applications of these kind of examples? And I feel like these examples I just showed are just scratching the surface of what's possible, because in a way, we have only used the response to temperature, right? So in this case that I just showed you of the roly-poly, of the swimmer, but we've also created, for example, solar panels that actuate in response to temperature and so on, and open up and close up like a flower. But I think the question here is that we're still stuck to temperature stimuli. Now, just imagine including in these architected materials other responsive polymers like hydrogels that swell when wet, or hydrogels that shrink when the pH is changed, or materials that, for example, respond to external magnetic fields and so on. You can now enable not just shape morphing and locomotion, which is what I showed, but also embedded logic by effectively pre-programming the materials to say, if wet and hot, swim, else, for example, hop. And I think there is a lot of opportunities for materials that embed this type of functionalities that span different fields of engineering, from the medical devices. Imagine deployable robots that can navigate through the intestine, for example, deploy certain grippers when pH is at a certain level, and then release drugs, for example, when the temperature is at another level. So I would say there's a lot of opportunities for these kinds of robotic matter in medicine, but of course also in space applications. In another work which was published this year from my group, we used the same idea of temperature trigger deformation in metallic 3D printed structures, which show the ability to do large bending deformation triggered by variations of temperature like the ones you see in the lunar environment. And so now you can think of having deployable systems or space deployable systems that respond to the large temperature variations found in space, for example, when the sun is shining or not, without the need for control systems or cumbersome battery packs and so on, which are susceptible to failure in complex or extreme environment. And finally, there's applications looking at, for example, self-deployable sensors, smart building technologies, and so on, where the ability to reduce the number of moving parts, controllers, motors, and so on, but enabling, for example, materials to deform as external environmental stimuli are provided would allow rethinking, for example, smart building technologies and sustainable systems. So these are the applications, but I mean, it's worth thinking, what are the biggest challenges in mechanics that robotic matter faces? And in this view that I just depicted of materials that combine structure with multiple responsivity, of course, we need to have multiple functions, like we said, response to, for example, water and temperature and light and so on, which sometimes requires having multiple materials. And that in mechanics gives us challenges in understanding the fundamental non-local coupling between the different deformations and how, for example, the superposition of these functions, the response to magnetic field versus the response to temperature can affect the stress and strain field in ways that are today hard to predict. There's a question of what is the impact of material chemistry and material composition on the mechanical properties. The question of understanding the fundamental nonlinearity and multi-stabilities, like the strain amplification I was mentioning before, that often is required or may benefit in being embedded in these structures for creating complex functions. And finally, is the question of design, which cannot rely exclusively on the standard topology optimization, but really needs to combine topology and materials optimization. And in my mind, really calls for advanced methods that are computationally efficient and data-driven in many cases. So this brings me to an end, and I want to thank you all for listening to my seminar. Thank the funding agencies that supported the projects you have seen. In these slides, and these are the students and postdocs at Caltech that worked on the different examples I've showed throughout the morning, and the collaborators that also, of course, contributed very importantly to all the findings I have described. So I'm happy to take any questions. Thank you so much for listening.
Thank you, Chiara. Chiara, if I may ask you to unshare your screen so I can bring our panel. Oh. Great. I would like to ask everyone, let's give Chiara a big round of virtual applause for the wonderful presentation. Okay, so if you would like to ask a question, there is a hand-shaped button. Please press the button, then I see your question. Then so okay, Glaucio, go ahead.
All right, thank you, Chiara. Very nice lecture. Actually, I was motivating my students in the last group meeting to attend your lecture, and I told them, I'll tell you just one word that will define her lecture: inspirational.
Thanks, Glaucio.
Thank you. So, yeah, I have a few questions, but maybe I'll ask just the first one, and then later we can discuss, especially related to the material in the beginning. Where you showed several microstructures, and also related to the generator part that is quite fascinating. One question that I have to you, what about the separation of length scales, Chiara? And that is also related to the armadillo design, all those designs that have microstructures.
Yeah, actually, Glaucio, you of course hit right on the hot spot. And I should have added that to my list of mechanics challenges in the last slide at the end. It's a very important question. And in a way, I have to say this idea of this growing, self-growing metamaterials that Chris developed is a way to answer that. So let me reformulate. One of the big problems that Armadillo has is that although we have tessellated the armadillo with different unit cells that have different geometries, the interfaces, right, between one unit cell that is designed via homogenization in one way and another may not necessarily respect the properties of homogenization, right? So you have this length scale dependent response that, although in an infinite homogeneous system would have these exact values of stiffness, density, shear moduli, you name it, in practice, right, it's something else when you have different interfaces, boundary conditions, and so on. And that's certainly a problem. Right now, the way the armadillo was designed is kind of, oh, it worked, it's great. But it wasn't an exact understanding of the interfacial properties of the different unit cells. We were just kind of applying compatibility conditions, which just means one unit cell has to attach to the other. So you have to have sufficient point of connection so that they don't come loose. But that's a very important point in an isotropic system or systems that use different geometries in the microstructure. So the way Chris has tried to approach this is to say, well, I can let the material grow that way. I don't have, I embed effectively the gradient in functional properties inside the microstructure itself. So I don't have interfaces, but I have an evolved microstructure that is more seamlessly connected to the different properties. And the preliminary experiments that we have done, it shows that in that sense, it's a little better at not having sharp interfaces. But then the question of how small should a unit cell be with respect to the size of the object and so on, it's still an ongoing open question. I think this connection of scales is a beautiful question that I think as a community we should look more carefully into.
Yes. Okay. Thank you.
Thank you.
May I ask just a follow-up? All the questions I have, they are related to scaling. I ask about the space scale, now the time scale. What happened is that I also, as you know, I have worked on these materials that are stimulated by temperature, for example.
Mm-hmm.
And when we are looking at applications, for example, then for practical applications, we need we need the system many times to respond at a time scale, let's say, that is fast, so that you can have several actuations on demand. What can you tell about the time scale of your actuation system? What are you thinking about it, let's say, to control the time scale of actuation, thinking about practical applications?
Yeah, I mean, I think you're right, and I mentioned these, when I was showing the example of the Lotus Leaf. I think when you look at temperature, you are diffusion limited. There are, temperature is a fine way to do examples and demonstrations. It might not necessarily be the best way to have something, for example, that swims repeatedly or actuates very fast, right? Perhaps in that case, having thinner structures and light actuation or magnetic field actuation, or basically an external trigger, which is not temperature, may be a better way to go. Now, that said, in many of the applications we've been thinking about, both in the medical field, for example, for smart stents or these robots that you can swallow that actuate in the stomach in response to pH and so on, you don't necessarily need an instantaneous, like, nanosecond reaction, right? You can wait a few seconds in releasing, for example, drugs or anchoring in some parts of the intestine. And I think in that sense, even hydrogels or pH, for example, sensitive polymers and diffusion limited polymers can do the job. Of course, other cases, you'll always need to see. We can't solve every problem with robotic matter. I don't think we're going to need to find the niche applications in which you'll find the right geometry and the right responsivity for each case. But I think some different actuation will make it possible.
Yes,
Thank you.
Yeah, welcome.
Okay, next question is from Qiming Wang from the University of Southern California. Qiming, go ahead.
Chiara, a fantastic talk. So basically, you show something like very natural structures that can self-grow, that can move under actuation. But when you look at those, like say, structures, probably like the stimuli responsive structures, right now people primarily focus on how to design chemistry, how to design new materials. But when you look at back, nature actually is different, right? You have some living cells and living components. Can you share some comments, how you vision how to integrate like living components into this kind of like synthetic materials, how to create like a growing or actuation structures like nature structures. Thank you.
Yeah, thanks, Jimin. And I mean, I think I have two-part answers for that. I think the first one is the thinking as a mechanician, which is maybe the way I framed specifically this seminar and this presentation to say, so the way I see it is that there's a wonderful job that our chemistry and chemical engineer colleagues, our material science colleagues are doing in developing an ever-growing number of responsive materials, responsive polymers. And I'm thinking of them as a palette of a painter, right? So you have different colors to choose. You have different materials that respond to different things. And you can choose your colors and then, paint your structure or design your structure a bit, making use of the available polymers, composites, and so on that have been developed and are continuously being developed, from chromophores to mechanophores to crystal elastomers. There is so many that we can choose from. However, you touch on something. The second part of my answer is that you touch on something that's very close to my heart and near and dear. And as we know, we've been collaborating on this, and it's something that is another aspect of this picture, which is, can we harvest some of these capabilities and functionalities from natural systems? Can we have responsive materials that are directly taken, for example, from living systems, right? And that our collaborative work with the with say plant cells and so on is something that has been looking into that direction, because I think sometimes there are limits in what synthetic chemistry can provide. And so the question would be, what about looking into biology as providing these fundamental building blocks that can respond to yet different stimuli, or can help us having, say, self-healing materials, which I have not discussed today, but they're also possible, or allows functionalities that have not been seen previously. So I think this idea of hybrid, let's call them bionic systems, may be yet another one of this color in the palette that will allow us to design architected materials with newer functionalities, just beyond mechanics. It's also, growing, responding, communicating, performing logical functions and so on. So I think it's a very promising and exciting direction.
Yeah, thank you.
Okay, next question is from Jordan Rennie. You want to go ahead?
Thank you. Wonderful talk, Chiara. It's always fun to see. So I appreciated how your first point you touched on was related to design tools. And it's something that I've been thinking a lot about, because it seems to me that one of the huge successes of 3D printing and the materials development that's associated with that is the huge number of parameters that we can now use to control things. At the same time, when we have a huge number of parameters, how do we design for this, right? And one thing I really liked was your time map over your 2D structure to actuate it at different times. Now, is it feasible? The question is it feasible to integrate the multiple kinds of responsive materials into that framework? Or do we need a different set of design tools every time that we're trying to, design for new functionality? I mean, I think of one example just to start the question is the mismatch between even just stiffness within polymers. We've done some work with hydrogels and silicones, right? And you can have, for sure, 2 orders of magnitude difference in stiffness, but much more than that is possible. So can you integrate that somehow with what you've already been doing for the time scale responsiveness? Or do you have any insight about a sort of coherent way forward on design tools to integrate these different aspects of materials? Thank you.
Yeah, thanks, Jordan. That's, as you know, my group is an experimental group, but we got so frustrated with the fact that the design part, it's so hard, because just by intuition somehow, like you said, there's too many parameters, that we started looking into design tools just to overcome some of the barriers. And I don't think we're going to have any time soon. I don't know if we're going to have by the end of my career, a universal design tool that allows us to combine all these difficult elements like time control, different impedances and stiffness between constitutive elements, architecture design, so topology, materials, time configuration, even optimization, for example, of the mechanical properties that are necessary for for certain motion or actuation, right? It's just, there's a lot of nested problems, one next to each other. However, I do think that data-driven approaches are going to be somehow part of this picture. I do think that because of the complexity and the number of parameters, we just need to rely on pre-computed databases. And that's what I've been hammering for the last 5 or 6 years, and just storing databases of materials geometries, whether for static or dynamic properties, which I did not discuss this time, but for wave propagation and other things, it's the same idea. Having somehow a pre-computed set of, say, hundreds of thousands of millions of geometries with different thickness, different shapes, different symmetries, and so on, which already tell us what kind of deformations, what kind of wave speed, what kind of, for example, bending stiffness each element would have, so that once you know what you want to build, you don't have to design it all the time. You just go back to your, effectively like a phone book, to your index of geometries pre-computed, and you just fish out what you need. So you only solve a reduced set of problems, which is this material compatible with these other materials? And again, I think it has to be a hybrid solution in which we use maybe more conventional optimization and, let's say, finite element computational methods, which, however, albeit precise, they are extremely computationally expensive, and won't solve the problem as they are. They won't solve the problem you've raised. We need to somehow have a trade-off between accuracy and, I would say, mechanical precision of having, say, a finite element, which is a converged system that we know gives us an exact solution proven with energy methods and whatnot. But we need to somehow trade that precision off with methods that perhaps are more either discrete or data-driven, in order to speed up, make them more efficient, so that more of these parameters can come together. So I think we will need a hybrid numerical approach in design that relies strongly on data, as well as in simulations that are more conventional to the mechanics community. I think there's, who opened, I remember a conversation that I had maybe 15, what was it? It was maybe 15 years ago now. I don't know, it feels like ancient history, with Pedro Reis, which was at MIT at the time. And I felt like, he was the one that says, well, why are mechanicians so stuck with finite element? Why don't we look at computer graphics as a way to speed up some of these, physics simulations, which maybe look good, but they're not exactly good as a mechanician would find satisfiably good. I think it was right. I think there is a lot that we can do in trading off, for example, accuracy for efficiency. And I think these data-driven methods are going to become the new FEM in mechanics. I'm looking 10, 15 years from now moving forward. And I think they will provide some of the answers you're looking for.
Great. Yeah, Jiga, go ahead.
Yeah, it's a follow-up on the previous question. Now, let's talk about examples we know very well historically. For example, since maybe 50, 60 years ago, people started to perfect the art of making integrated structures for microprocessors, right? Highly integrated after decades. Lots of people can contribute. I think lots of people can contribute primarily because the thing has a high financial value, economic value, and also structure more or less have a clear structure. So people can worry about an interface, how to integrate the metal and the ceramic, the plastics, right? And then this morph to MEMS. So in the early days of MEMS, I was just confused. There's so many different principles, optical and thermal, magnetic, they're very confusing. But nevertheless, there are a few useful things came out of this. Now you have a morphing structure. I guess it's a MEMS 2.0, right? It's a more flexible, but essentially what you call robotic matter. So from these previous lessons, can you say a few things about the challenges, especially to mechanics and materials people? What do you see are soft spots, maybe hard problems for us to address at this? So there's a historical record. People can make very complex structure, and the structure can even morph, can even be useful, can even create economic value, not just getting funding, right? Also produce money. So there's a historical record.
Well, I mean, I think Jigang, you're absolutely right, and I think we are standing on shoulders of giants in that sense, especially when it comes down to shape changing and morphing materials. I mean, look at the wealth of work that John is doing. For example, John Rogers is doing on these multi-scale morphing systems and so on. I think what's different in this case, or at least what's different in my mind in this case, is this multifunctionality, is the fact that we want to combine responsivity, not to just one stimulus, which is, for example, a force applied to stretch or a temperature to morph, but the ability to have some materials that combine, for example, a response to different external elements. Is it hot? Is it wet? Is there a magnetic field around me? Or is the pH changing? And all of these aspects are causing basically competing, often incompatible stress and strain fields inside the material, right? That's not what you see in the conventional MEMS or shape morphing systems, where usually everything is designed with one material, okay, be it temperature, be it water, you have a morphing and you're done with that. Here, I think the biggest challenge is this dealing with this combination of fields, functionalities, and overlapping constraints, which, in a way for mechanicians is a bit of a challenge, right? Is understanding this competition between different responses. That, of course, I mean, I'm expecting is going to lead to potential nonlinearities, incompatibility, whether geometrical or materials, which is something that they're always a challenge to model. Now, so that's to ask, your first question. If you tell me what is the biggest problem, you see, that's maybe the biggest. And then there is the details that, how do we design? How do we make different materials stick together? So this compatibility of interfaces that Glausio and Jordan kind of both brought up in the conversation earlier. But I think all of these in my mind are solvable. I find I find the challenge perhaps of these designs of stresses and strain field to be for mechanicians maybe the central point. In terms of applications and generating revenues, that would be nice. Wouldn't we want to all? But I think I am genuinely optimistic about, for example, the medical field. A lot of these materials and devices that can respond, sense, and react to temperature, pH, and so on. I think we will see more and more of them used. Already, if you think about it, think of the stents that they're used for cardiovascular. They have been around for a long time, and in a way they are shape morphing materials, right? So here is the question of, can we make them smarter, right? Can we make devices like these that now, rather than just expanding when they're in the body, for example, they can anchor in specific points, they can morph according to the stresses around them. Not all veins or arteries are straight, right? Maybe we can have smarter stents that can conform to the stresses and strain applied by the surrounding tissues, in addition to temperature, in addition to pH, in addition to many other things. I think there is space to really make impactful advances in that sense. Smart building technology is something where we've been thinking a little bit as well. But I think there is space for applications that go beyond the intellectual curiosity.
We have Professor Bazan from Northwestern University joining us on the panel. Go ahead.
Chiara, fantastic, inspirational. I have just a brief comment, actually. In many of these applications, reliability is an important issue. Now, it is generally believed that for engineering applications, the failure probability should be 1 in a million or less. Now, interesting about these architecture materials is that they totally change the distribution. They, for example, show a material with some certain architecture structure that is much stronger, 15% stronger in the mean, but it's order of magnitude weaker at the probability limit.
Mm-hmm.
And that's something that has been left out of consideration, although it is widely, of course, acknowledged in probabilistic circles. But that's something to pay attention to, because we are working on applications for engineering. Some other applications may not need it, but most of them that you mentioned would. That's all.
Yeah, Zdenek, thank you so much for your comments. I think you're right, and I think this is something that a lot of the 3D printed components, parts, materials, and members right now. This is something. The cycle resistance, fatigue resistance, reliability is something that we as mechanicians need to be very concerned about, especially for applications where, you know, the loading conditions have to go through hundreds of thousands, millions of cycles. The lifetime of these 3D printed, let's say, structured materials, but in fact, even any 3D printed part is a concern, because today, although we have many 3D printing approaches available, they also introduce a lot of defects. So it's an important point. That said, I think some applications, for example, applications like in the medical, think of like this idea of having a robot that you swallow that deploys, anchors, and releases, for example, drugs at will at specific locations. You know, it doesn't need to go through millions of cycles. You know, it has to work for a day, for 2 days maybe, and then it can leave the body, right? So I think the question of reliability always depends on specifically what problem are we solving. Are we trying to build something that has to be in the body for 10 years, like a stent or more? Or are we think of something that should biodegrade and eventually be removed from the body after a few days? I think it's a question that has to be answered to the specific applications. And today, although I showed some gimmicks or gizmos as examples, I feel like we're still exploring the fundamentals of how to design, how to predict stress and strain field in this complex architected and multifunctional structures. So I think we're still more on the discovery level and fundamental science level, more than at the level of, okay, can this sustain a million cycles, or reliability for engineering? I think that's the question that we need to be concerned, we need to focus on, but it needs to be application specific.
Okay, thank you.
Okay, next question is from Manish Singh. Manish, go ahead.
Hi, Dr. Daraio. Thank you for the very interesting talk. And my keen interest in your talk comes from my work using shape memory polymers for drug delivery. So I have 2 questions, and based on how much time you have, you can just go ahead and answer either one of them or both of them. So my first question was that you sort of showed the work on shape memory polymers, and based on the fact that they are only one way, you sort of switched to liquid crystal elastomers. But what I see is that both of them are temperature control, and this on the time scale that you show, they both respond on sort of an equal time scale. So my question is, did you explore the use of 2-way shape memory polymers? And if you did, then what made you switch to liquid crystal elastomers? What were the advantages that you saw in them, which you didn't see in 2-way shape memory polymers? That is my first question. And I'll just go ahead and say my second question also, that when it comes to using for medical devices, these shape memory polymers need to be temperature controlled. So how do you envision maintaining that temperature control inside the body. If it's using the body temperature, then the device will automatically respond the moment you put it inside the body. So yeah, these are my two questions.
Okay, so thank you for the question, Manisha. Nice to meet you. I think so. I'm going to give you, maybe answers that are not going to be mind expanding. I mean, the reason why we chose the shape memory polymers is just because we had the Stratasys printer available in the lab, and we saw it worked, and we said, great, this is going to be the perfect demonstration of the concept. So although there are other shape memory polymers, like it was a simplicity and pragmatic approach to say, well, what would be the simplest way to do a tabletop demonstration? And we picked what we had available in the lab. This idea of the painter that picks the colors that are on the palette, and you kind of go with the ones that are available. Now, I think there are other solutions. I think, for example, liquid crystal elastomers can also respond to light. And the light actuation has been shown, and in fact also modeled, to provide faster cyclic actuation. So you really can get a rapid clock, if you want, or repetition rate on relatively small and thin members. So you can use something other than temperature, if temperature is a constraint. And this kind of goes into the second question, which is what do you do in the body, right? And I think in the body, we need to be clever and use multiple responsive elements. So it can be temperature, but like you say, that's, once you insert it, it's going to be at 37 degrees. So it will actuate at a certain point. So that's where you want to add, for example, pH response, right? The stomach is a great example in which the pH variations are large, and so you can target specific areas for actuating, for example, grippers to anchor things where you want. We'll be looking, for example, also at materials that respond to external ultrasound. So imagine having this small robot that actuates with temperature at 37 degrees once you swallow it, but then also actuates with pH once it reaches a certain part of the intestine. And then it also actuates other functions when an external ultrasonic field is directed, right? So you can use other stimuli. You just need to create this complex architected material in a way that different parts actuate in different times when the different stimuli are provided. So go back to the question of, gee, how do we design this? And then you loop back to the beginning of the seminar, which is, okay, we need to figure out a better way to efficiently combine all of these different materials, different structures, and so on. But I think the answer to your question is, well, you need to not just be stuck to temperature, but look at other responsive elements as well.
Sure. Thank you. And the example that you used of ultrasound, that makes sense because we use ultrasound to do that. So right. Yeah,
it's also non-invasive, right? You can use light if you want, but then you need some kind of a tethered approach.
Yes. Thank you for your answer.
Next question from Tian Chen. Tian, yeah.
Hi, Chiara. Nice to see you again.
Nice to see you too.
Yeah, it was a great presentation, obviously. But my question is a bit philosophical. It's like we're increasingly embedding these intelligent material or responsive material in our design. At what point do we kind of transition into the mode of MEMS and then to full on robotics? Like, how do we define? Why don't we just assemble a bunch of components with motors? I always ask myself this, right? Why don't we just build a robot that can swim? And then, yeah.
I mean, I think I always go back to, and I think you're right, Tim. And I mean, you know this work because you were part of it better than I do, probably. But I think, to me, at the end of the day, sometimes there is no either this or that. I think, often the solutions are going to be a hybrid, right? So, part of the component will require a battery. Part of the component will require control systems that are similar to the ones we have for conventional robotics. At the same time, I think conventional robotics today can benefit on, smarter material systems. Right now, you look at a robot and there is so many moving parts, so many assembly points required, so many joints, cables, members that require, which are in a way clunky and not always reliable or as flexible and as, let's say, widely applicable in different areas of the bodies. I'm thinking, you don't want to have a rigid robot, or I would not want to swallow a rigid robot if that was the choice between that or a soft, formable robotic system. There's a question of, also reducing the complexity of conventional robots. Like if you have materials that autonomously respond and perform actions, you require less programming of your robot, you require less failure point, you require less components that either need to be integrated in the software, thinking of the control systems, or just hardware that needs to be connected. And the smaller you make it, the more prone to failing and difficult and expensive to fabricate it's going to be. So I think the more we can make this material passively reacting, the more reliable they're going to be, the more, again, applicable and compatible to the human body, I believe they're going to be. Now, I think we're going to be limited on how much complexity you can embed into the constitutive materials and the structure itself. And so then if you need something that really does something complex, like transmit a signal to an electronic device outside the body, right, to communicate to my cell phone, you're still going to have to go back to the conventional electronic systems, sensors, maybe MEMS and so on. So maybe at the end of the day, the answer is a hybrid system where we have smart, responsive, robotic material working together in unison with the more conventional robot itself. But I think robotics, and I talked to a lot of robotics colleagues, I mean, robotics as a field is thirsty for materials that can do more than provide structural, rigid support. And I think that's where, as mechanicians, we can think of improving those designs to make robots more independent, more lightweight, more flexible, soft, and compatible in a way to human life and human body.
Yeah, that makes sense.
Okay, next question is from Catherine Ding.
Oh, hi, Professor Dario. I'm Catherine. I'm a PhD student from Katya's group and Professor Chris Redcroft at Harvard. Thank you for a great talk. I learned a lot from your presentation today. I have two questions, one more technical. I guess as Professor Bazan just mentioned that it is very important to design these type of materials that are robust to like failures, and especially for, I guess, for these kind of programmable materials where we go to nonlinear region, they are very sensitive to localized failure where they just break. So I was wondering, do you think, I guess it is also an application kind of specific question, but would you please highlight in what kind of specific application it will be more beneficial to purposely design weak joints such that we have like dedicated area for it to fail, so it is in a more controlled manner, or in like what kind of application it is more crucial to ensure that we develop better bonding techniques such that they don't have those localized failure?
Yeah, thanks, Catherine, for your question and for listening to the seminar. It's nice to meet you. I think you're right. I mean, I think we need to be, another aspect that I think is very important in this design of, let's say, structured materials, metamaterials, however you want to call it, is designing strength to failure. And that's actually an aspect that I haven't talked in this seminar, but one of the students in my group, in collaboration with Kaushik Bhattacharya, has been looking at very attentively, is to say, can we design strength and decouple it from stiffness and density and so on? And I think it's an important point. And there are, in fact, applications in which you do want to design fracture to occur, like guiding fracture or timing fracture. Think of, again, I mean, I keep going back to the medical devices, maybe because that's what I have in my mind most often these days. But I think of areas in which we talked about the example of the anchoring robot that releases drag, right? Let's imagine that you've swallowed this robot. At some point, this is anchored, And then you want to get rid of it. And what are we going to do? If it's anchored there and it's too reliable and too strong, you're going to be stuck with having this thing in your stomach for days on end, right? That's when you want to be able to say, you know what, I want fracture to occur at this point, at this time, right? That way, the body can get rid of it. It can basically, once again, perform an additional function, which is I'm done with what I had to do. I delivered, for example, my cargo. I will go. And I think there's other examples in which, even for, we were thinking about robots for remote explorations, right? So you can launch these little devices that kind of swim to remote areas. And at some point you want them to break apart. You want to somehow not remain in the environment, right? Whether it's biodegrade or whether it's because you want to dispose of them. And I think the ability to control fracture at specific point is a very interesting fundamental mechanics questions and design question, but it's also practical in specific applications, like the examples I gave you. It's something that perhaps it's been less looked at, but I think it's because it's hard to do it and not because it's not interesting.
Thank you. And sorry, if you have more time, I would like to ask my second question. I guess it's more like a general kind of philosophical question that I guess this field is very exciting because it combines science and engineering applications, which is a very interdisciplinary subject, which is also what I'm very interested at, because we try to program and optimize like textiles to make it like smarter in a way. So I was wondering, in your experience of convincing or motivating other people this is an exciting topic, do you think that more people conceive it as like a scientific question, or more people conceive it as like an engineering practical question? Because I guess like there will be like different sides, and I was just want to hear your perspective on that.
I mean, I think as a community, you're touching on a very sensitive point, because as a community, we need to ask ourselves the question of what problem and whose problem are we really solving? And I think, in academia, there is space to explore and let your creativity and imagination run wild, because, you may just find something that you didn't know it was useful, right? But it becomes useful maybe decades from the day you discover. So there is that aspect. So this curiosity-driven science that pursues research directions that are not immediately applicable, I think has a reason to exist and should continue to exist. At the same time, I think that's something I ask myself often, maybe, after a few years in academia, is the question of, okay, but I want to solve a problem somebody has, right, besides this. And I think, I don't know if one is better than the other, and one has more merit than the other. It's a question of what drives your passion and your, why do you get up in the morning to pursue research? And I think there is space for both. And I think if I look back at my own academic career, I started very much focusing on the former. So focusing on, I'm just want to do curiosity-driven science. I'm there for the innovation. I don't care about application. I just want to be effectively more of a scientist engineer that invents things that are there, but are not necessarily useful for anything. If I look, 15, 20 years from the day I started today, I feel more driven towards solving problems. And so there are other projects in my group today, which I didn't have the time to discuss, which are much more anchored to, I want to solve this problem now, right? Whether it is, I want to model, a network for COVID more precisely, or whether it's, I want to design a temperature sensors that we can all wear to measure fever and not have to socially distance ourselves. There is space for that too. And maybe today I guess my heart is moving closer to the engineering side of things, but that doesn't mean that it has more merit. It's just whatever drives your passion, I think, should be what you choose to pursue at any given point throughout your career. And I think in this specific example, both arguments are valid. Like, do you want to solve, so you can collaborate with roboticists and say, I can help you do this with robotic matter. Or you could just say, I want to answer the question of nonlinear stress strain functions and just delve into the science of it. Both have equal merit. You just need to pursue the one you like.
Thank you.
Thank you, Catherine, for asking 2 questions, especially the second one, which is well in line with our discussion with Chiara before the seminar. I think this is a very unique feature of EML webinar, that the discussion like this, which is not typically seen in other technical webinars, and that added a lot of value for EML webinar as well as for the community. Next question, Jimmy.
Thank you. Wonderful talk, Chiara. I actually agree with Glaucio as an inspirational presentation.
Thank you.
So you mentioned that you are actually, I'm particularly impressed by this self-moving thing on the hot surface. I remember when Matten City gave his webinar, he mentioned that there's computational intelligence and physical intelligence.
Yeah.
Physical intelligence is something that you don't need neurons, you don't need computer power. It just, intelligence is there. It rolls and rolls. But nevertheless, this requires design.
Yeah.
Okay. And you mentioned that you can have multiple types of stimuli, thermal, magnetic, HP, or whatever you want to. But even when you introduce these things, your system, again, becomes more and more complex, generally speaking. And you have to design your system to respond to each of the stimuli to achieve functions, a particular function. And the key word over here is design. So my question is, can you imagine something that can reconfigure itself, even for a single stimulus? Wind blows this way in the morning, blows that way in the afternoon, right? So is there a system that one can envision that would reconfigure itself based on whatever sensed information you get? If so, what type of system, that type of design or type of system that you should build?
But Jimmy, I mean, that's a good challenge for a couple of PhD theses. I mean, I think it's possible, and actually external loads, like you said, winds or currents in water and so on, are certainly something that maybe are very accessible, right? Can we have something that reconfigures? To a certain extent, this has been also the holy grail for a lot of my fluid dynamics colleagues, that when they think about reconfigurable wings and shape morphing wings for aircrafts and drones, where you can change shapes depending on basically fluid flow around the structure. I think there is space for that as well. I mean, I think there the challenge becomes really the question of also looking at not just the shape changing, but the question of strength. How do we design something that is able to change shape by a lot, so the form, and hence find basically architectures that allow us, for example, to buckle or bend or reconfigure depending on wind or flight speed, let's say, or different fluid dynamical profiles. But I think there's a question of also supporting sufficient load and so on, which makes the constraints on this design even harder. I think one challenge which I keep also bringing up when in discussions with students and so on is a question of, for these morphing elements, if you truly want to have control, we need to have the ability to design for buckling, we want to be able to design for complex, shape morphing. We can bend things, and that's fine. We can show, albeit complex interwoven architecture, but they're still based on bending. What about designing for buckling? What about really trying to go to this non-linear side of the analysis that we all, at least we as in my group, shy away from, because they're hard to predict, they're hard to model, and let alone design for. But I think that's something that's perhaps where we need to look for to answer your question, is to say, well, if we want to respond to large loads and we want to truly have shape morphing that can be used, say, for wind turbines or drones or so on, we do need to look at large deformations and nonlinearities. And that's something that as a community, I think it's a hard question to answer, but it's one we should look more. And perhaps, the exploration of instability it's a step in that direction. We just need to do it in a way that's not just on periodic system and on relatively simple structures. We just need to learn to do it in more complex architecture that are perhaps non-periodic and non-uniform.
Yeah, another direction maybe you may want to consider is what you mentioned before, and actually it's related to Ken's question, hybrid system. So you do have some motor that would allow you to control the system to reconfigure itself that respond to a different type of stimulus.
Yeah, I mean, I believe in that. I think that there cannot be just the material being entirely the whole machine. I think we can make materials that can do more than just being passive structural support element. I think we can embed part of the complexity of control systems today that limit a lot of the functionalities in robot. We can answer those questions with materials, but I think integrating them with more conventional actuation is going to be the key, at least for complex shape morphing, wing morphing or reconfigurable structure morphing cases. Again, as the complexity increases, we cannot just rely on constitutive elements in structured materials.
Very good. Thank you. Thank you very much.
I would like to introduce one of our panelists, Dr. Steve Cranford, who is the editor-in-chief of Matter. And Steve himself is a mechanician as well, also published a very interesting and nice paper in EML previously. He has been sitting in the panel quietly. And Steve, do you want to say a few words?
Well, thanks for the introduction. I'm glad to be here. It was a great talk. I also have another paper currently under consideration at EML, so fingers crossed that that one is reviewed well. In terms of today's topic, I mean, it's great. It's inspiring. I really think we're at a renaissance of this morphine matter. And I think what you're doing in particular, it's almost like you're making the simple machines, pulleys and levers that will perform the fundamental operations in more complex systems. So nobody knows really what the future will bring, but it's very exciting in terms of how we can design these mechanisms to put in to solve more complex problems. Or, the people who developed the first combustion engine probably didn't envision today's modern automobile, right? So what you're doing with the little swimmers or these little mechanisms, it's really fun figuring out the fundamental problems, what we can do, push it to the limits, the failure limits. So it's very exciting, and I can see a huge future. And yeah, the trick is, what's the problem to solve? And I think the biomedical range is exactly where we should be going now. So I mean, that's why I definitely wanted to listen in today to see what your thoughts on the matter, and see what's upcoming. So it's very exciting. So hopefully maybe there might be a submission or two that comes not to EML, but maybe our way. But we'll see in the future.
Thanks, Steve.
No problem.
Yeah, thank you for bringing this friendly competition here. Next question is from Sulin Zhang from Penn State University. Sulin is also one of the editors of EML. Sulin, go ahead.
Chiara, very nice talk. So my question is about hard and soft. And I think that hard material is more difficult to actuate. I think the fundamental principle of your design, say if I'm right, is a computation of input energy and activation energy barrier. So generally hard material, the activation energy barrier is higher. So it's more difficult to actuate. So if you look at the nature material, like our human being, right? So you see this is a hierarchically actuated system. So motor proteins actuate each cell, muscle cell, and the muscle cell collectively will pull the muscle and pull the bone, which is very hard, right? So this also underlines the design principle of your materials and your machines, the synthetic machines. So are any people looking in this direction? That is, activate hierarchically each building block, which is soft, and go all the way to the hard material to make a hybrid structure that we are talking about?
So Sulin, you are completely right. You know, we keep thinking about the question of like, how do we go from an actin filament to an elephant moving, to a whale swimming? You know, this is phenomenal. It is truly the result of a collective motion in a hierarchical design that combines structural elements like bone that are, you know, relatively to actin hard, you know, stiff and heavy, with elements that are effectively soft polymers that taken in and of themselves have really poor mechanical properties. And the answer is hierarchy. So to answer your question, I'm not aware of anybody that's been able to demonstrate in a synthetic domain this kind of behavior. I think though that's exactly the direction we need to look at. I think you can't just have metallic system or hard and stiff structural system and expect them to somehow self-morph and shape into complex architecture. You know, we've been trying this. In work that I haven't shown today, we looked at bulk metallic glasses strips, for example, that start from a stiff and, you know, relatively rigid material in the bulk, but if you make it thin enough in foils, it becomes so flexible that, you know, can expand in volume in an enormous amount. You can basically make this ribbon curl into a tiny space and then deploy into large structures. So there is something you can do even with stiff materials when you control the aspect ratios, the flexibility, and so on. But I think the combination of these materials with soft structures to actuate, it's going to be the key. And I have not seen much work in this direction because it's hard to do it. But I think it's certainly a direction we should explore more. I'm particularly excited about that because for some of the more, let's say, macroscopic application, think of building technology or lunar landers and so on. I mean, we need to go to metals, right? We need to have structures that are more rigid and more load bearing. So being able to learn this hierarchical design of actuation is going to be key. It's something I would like to look at in the future for sure.
Yeah, just to follow up, probably Qiming have mentioned about that. I know that a lot of chemists just isolate these proteins, the motor proteins from cells, and put in a synthetic gel and activate the gel. So this is the simplest, probably the simplest hybrid material.
That's right. Yeah, and that's maybe kind of echoing Qiming's comment before. Like we can look at harvesting molecules or more complex organisms from living systems, whether it's actin filaments or chloroplasts or cells or bacteria. Like, you know, I'm thinking when I was a student, I remember the work from Angela Belcher at MIT, right? Looking at how you can synthesize material using viruses and so on. I think there is a lot that these hybrid systems can do for us. it adds the complexity that biology adds, right? Which is now we have yet this other, let's say, difficult to control component that we need to design for. But we can certainly learn from how nature does things. And if we can also incorporate some of the natural biological components for actuation, great. I think it just adds yet another level of complexity in the design that we were discussing before. But I think it's something we should look into definitely more.
Great, thanks.
So next, I would like to introduce another panelist today, Professor Vicky Nguyen from Johns Hopkins University. Vicky is current president of the Society of Engineering and Science. And indeed, we have another past president sitting in the panel as well, Professor Glaucio Paulino. I believe, Glaucio, you served in 2018, right? The president of SES.
Yes.
The SES annual meeting is one of my favorite conference and meetings to go. And I'm quite sure many mechanicians share the same view. And I like it too much. And I actually helped co-host in 2016 with my colleague. So Vicky, do you have a few words to say? Let me mute yourself.
Oh, sorry. Yes, I do have a question for Chiara, but since you gave me the opening, I will just say that we are still going on with the SES 2020 conference. It will be virtual this year. And Hanjin Zhang, who is on the editorial board of EML, is the conference chair, and he's doing a fantastic job putting the pieces together. And you will hear from us soon. I think it's a very exciting adventure, and I've just been really excited by the level of enthusiasm in the board this year to express the need to continue the community and the fellowship of our society, and to have this meeting online. So stay tuned. Okay, so now I get to ask a question. Chiara, that was a great talk. And my question actually follows Jordan Rainey's previous question. I think these materials and their multifunctionality, and not just in the material, but actually in the interaction with the environment, like you talk with contact and such, are complex, and our traditional modeling methods are really challenging. We're trying to do exactly some of these things, right? And we're running into problems with Abacus, with my own custom code, and we're trying other codes, and it's really hard. And and there are two kind of thoughts about how to do modeling. One is to do rigorous. Well, I guess one is to do heuristic. Let's put together building blocks, and let's from this building blocks do design to get this structure. The other is, from topology optimization, trying to really rigorously through math to prove that these designs exist and can be designed. And I'm wondering, what your thoughts on that is, and also how does machine learning fit into this, and how your experience with machine learning and how its contribution to this. So I'm thinking ahead that yes, we can then design these morphing structures, but eventually we want to put these designs, motions together to do path planning, right? To do control, to not just to get them to move from A to B, but to move from A to B, turn, wait, turn again, drop their cargo. And to do that, I just don't see how we can go about, with our rigorous FEA detailed codes to get there.
Yep. Vicky, nice to see you. I agree. I mean, I share the frustration, and believe me, maybe even more so being an experimentalist and having to navigate through, design these things that work. You just can't just think them out of the box while you're washing dishes. It's like that doesn't work that way. I think having systematic design tools is going to be key. I think we do, as I mentioned before, we do have to trade some of the rigor that we are taught as mechanicians to pursue in modeling. We need to trade that rigor off, and the accuracy and the exactness for efficiency, because like you said, finite element alone is just not going to cut it. I think where I find a possibility for hybrid methods, like you mentioned machine learning, we used machine learning in some of the projects I showed today, like in this data, for example, fitting of the temporal response of the bracket, right? So that's how we train the methods to fit all these hundreds of experiments that Connor performed for determining the response of each one of these tiny little brackets, so that once you know, you can place that little bracket in the right place in the architecture and then get the piece of architecture to bend at the right time, right? So if you just think of machine learning, it's a great fitting tools that when you have large amount of data, like in the examples I just showed, we came from an enormous experimental campaign, which I haven't even, scratched the surface of. I just told you the results, but it was like months and months and months of hundreds of different experiments. I think that there is a need to rely on pre-computed data, both in terms of design geometry, structures, members architectures, 2D, 3D, which we can't just solve ad hoc for every little problem we're all trying to design for. We just need to have a shared database, basically a certain, I really think of it as a pool of geometrically pre-calculated or pre-characterized shapes that I know I can go back to in my database and say, if I need something that bends 90 degrees, here is the plethora of possible, unit cell options you can pick of, or the plethora of different geometries that your problem may benefit from. And then maybe at the different scales of assembly, combine these data-driven or pre-computed data methods with more conventional methods. I think where neural network can come into place is the example I showed at the beginning of the seminar, where there was this closed loop computational laboratory, right? Where I say, well, but I'm gonna need to constantly compute or expand this database if I want to account not just for the geometry, but also for the response of the system, for the buckling, for the acoustic, response and so on. And that's where having basically a closed loop of generation, evaluation, so design a new generation and so on, it's just going to be there for you to constantly in the background create and expand this database of resources that then everybody could tap into to say, oh, now I need to build, for example, a new frame for my glasses. What can I do that doesn't have to have hinges? Like, can I have a metamaterial to do that? Or I want to do a running shoes or a helmet or a robot, or what is it, whatever it is that you're trying to solve. But I think we kind of need to have a shared ground of resources. Like we all share codes of finite element, it's going to be a shared database of pre-computed geometry and functionalities that we can all tap into to then come into these more complex design approaches. Because if you want to redesign everything from scratch, it's just too many parameters. Jordan mentioned that before. There's just too many things. You want to design for materials responsivity. You want to design for structure. You want to design for nonlinear stress fields. How are we going to do that? And I think, again, hybrid approaches where we trade rigor, for example, for prior data or for approximate methods like computer graphics does, are the way to go. But it's hard. I'm not saying that I have an answer right here. I think it's what we should look at for design.
Yeah, so what you're arguing for a systems level approach, which I completely agree on, but perhaps we can also think about ways of doing reduced models or simplified models.
Yeah, I mean, the reduced models would allow us to say, well, let's discretize the domain and forget about modeling the entire unit as exactly with stresses and strain, but I'm just going to take a subsection or a sub element of my structure and say that's a point and there is a spring. Mm-hmm. And that's a little bit what we did with the model I showed for the ribbons and the lotus leaf. There is more to be done. I think we can do better than that, especially when we want to combine these multi-scale designs where you want to model the bracket, but then you also want to model the entire robot, right? And I think this reduced order model will have to be part of the picture.
So let me make a comment over here. So I think that's precisely where machine learning would be useful, simply because the system is too complex. When you have a very complex system, you need to model each aspect of that, whatever tool you use. And in order to do that, you have to have a model, elasticity, plasticity, all these type of things. But machine learning, it doesn't care what model you use. It learns from your either your behavior or your experiments. So I think that's where perhaps the machine learning tool would have the biggest impact. I believe Teng made that comment several webinars ago.
Yeah. So Jimmy, I can follow up the comment on here. Also, Vicky's question and Chiara's response on the machine learning aspect. For example, Chiara, you showed one of your part of your presentation. You showed that you have these building blocks, and then you have this growing model to allow this using the building model, the building blocks to grow using programming into a material with desirable stiffness and the Poisson's ratio. You had a plot with this 2D, with X being the stiffness, Y being the Poisson's ratio, negative Poisson's ratio, with many data points over there. I assume each data point in that plot actually correspond to a specific model you grow, right? So I think that's probably one of the aspects that the machine learning can help over there. I do see a challenge here. The challenge will be, how do you extract the connectivity between the building blocks into those so-called descriptors for the machine learning? Because machine learning algorithm deal with numbers. So you need to translate those connectivities between the building blocks into the descriptors. So then you can turn the crank of the machine learning algorithm to help you to accelerate the growth process and accelerated growth to connect the lattice structure to the desirable property of this architecture.
Yeah, I mean, we've been thinking a lot about it, Teng, and I mean, in part, I'm part of a group of the NSF cyber infrastructure proposal that's led by Kate Brinson at Duke and several others, Wei Chen, Cynthia Rudin, and so on are part of it, in which we're really trying to answer part of those questions, right? I mean, but it's non-trivial, because right now, even the question, like a fundamental question when you think about machine learning, of what is a geometry? Like, I have an object, right? That said, this is my architected lattice. I have many here in the office, and you have. How do you tell the computer that this geometry is this geometry? I mean, sure, you can voxelate it and say, oh, this voxel has material, this one. Good luck with that. You're gonna have a gigantic, file for. So how do you tell the computer this point is a geometry, and this geometry is what corresponds to this? There is many different geometries that comes from, say, there's not just beam-based metamaterials or structural materials. You have plate-based, you have isogeometric curves that now people design metamaterials with or structural materials with. And even just defining a unique way, an interpretable geometry that the computer understands and relates to property is a tricky question, which, we've been a year and a half, 2 years into it, we haven't quite completely got control over. So I think machine learning is a wonderful tool. I don't know if we can today find a way to create a universal way to define the structure to function or structure to property relationships. But, we can do it on subsets of geometries. For example, geometries that are beam-based, geometries that are plate-based, geometry that are, for example, multi-material composites, and train different algorithms to understand the fundamental rules of designs. It's tricky though, and it's right now a research direction that I see growing. There's more and more papers coming out on the topic, but I think it has a lot of room to grow and a lot of room to improve before it can truly fulfill design purposes like the one we need, for example, for robotic matter.
Yeah, I think that's a very interesting aspect. And actually, as Jimmy mentioned, it tripped in quite a few times in the past EML webinars, like in All Sigma, the topology optimization, and a few others. Now, here's another feature of EML, which comes very convenient to help us to sort through all these discussions. All our EML webinars are recorded and made freely available through YouTube channel and also Weibo. And we have another new feature already in place. We invite every EML webinar speaker to submit and publish a EML overview in extreme mechanics letters. So far, Jigang, how many we have? We have 4 published so far?
5.
5. Okay. The reason I'm asking is because the turnaround time is quick, typically a few days, less than a week, and the speakers will summarize the topic, and I think the discussion, long-term discussion in different aspects during the webinar can be also summarized in the overview. So that's another feature becomes very convenient for the other people who cannot join us live. And also you can cite this paper in other relevant publications. This makes EML webinar very distinct from Gordon conferences as well. Okay, I do see Glaucio, you have, go ahead.
Yes, can I make a couple comments? Because I hear a lot here about hybrid approaches and about machine learning. And I feel that we need to be careful. Because, for example, I go in meetings and I see many people saying machine learning doesn't care about the mechanics. Is that right? I mean, is this a good thing? You know, if we extend this line of reasoning, at some point our field may even disappear, maybe hijacked. I can see that on the students. Many times, for example, I can see a trend now. I think all the things have consequences. I see a trend that many of the students now, they don't have that rigorous mechanics that I would be looking for. And for example, some time ago, is related to our work in machine learning with topology optimization. And I discussed that a couple of weeks ago in Ole's talk. What happened is, yeah, that's the idea we had. We don't care about mechanics. Let's just do machine learning. And then what happened is we were working with the displacement fields. But then rigid body modes are included in displacement fields, and we were generating rank efficient matrices and results that more or less make sense. But at the end, they make no sense when I understood them, but more or less they made sense. Then when we change all our machine learning framework to be based on the strain fields, for example, we could eliminate that rank deficiency. So I have a problem when I see that for many different points of view. And that is also related, it's not just machine learning. Machine learning is a tool, mechanics is something fundamental, it will always be there. And it's very easy to solve simple problems that look great. What about the tough problems? The real mechanics, the fundamental mechanics cannot go away. Cannot go away, we need that. Also, with hybrid approaches, we need to be careful. Yes, it's great to use computer graphics, it's great to use other fields. However, we need to be very careful. For example, it's very easy to use codes and software from computer graphics, for example, where you see physical-based simulations. And there are even journals based on that, physics-based simulations, where a lot of the mechanics principles are being violated. Even angular momentum, for example, in dynamic simulations, totally violated. So sorry, but I couldn't hold myself. I felt I needed to say that. Sorry about that, but.
Glaucio, I think you're right. I think there will always be space for mechanicians, and this is not in any means, I think, a way to threaten the community or the field. I mean, I think there has to be a space for both things. I think to me, so first of all, I don't believe in having the black box machine learning. I think it works great for fitting data from experiments. You know, maybe that's what we're going to be using it for. Sometimes it's just we're going to get better readings out of experiments. You know, like having, for example, better DIC tracking, better. You know, you can do a lot of things with better fitting. Like by all means, we shouldn't discard that. I think. However, there is a lot that one can do by embedding physics-based principles in some of these data-driven techniques that are not just black box, but they employ, you know, physics-guided algorithms and equations into or to basically guide the interpretation of the data. And I think that's something we need to look carefully at. I also think that there is two different aspects that you touched upon, right? There is the fundamental mechanics that we can solve rigorously, analytically, maybe with finite element, which, like you say, they're simpler problems, right? We can look at the stress field around the plate with a hole and solve that very beautifully, but they're not going to be able to be used completely when you have such complexity where you start having multifunctionality, multi-material, large deformation, non-linearities, and you know, maybe dynamics embedded into this whole thing, right? And so that's where you need to start to, in a way, be tolerant to other methods that are, let's say, compatible, but not as rigorous. Because at some point, if my goal, it depends on what your goal is. Is your goal to understand the mechanics and the stress field exactly? Or is your goal to have some kind of, you know, shape morphing device or gizmo that moves? And I think if one works making some approximation, albeit not as rigorous and analytically provable, then, you know, let's use them for design. It's okay. I think we can test the validity physically, either with experiments or with reduced simulations on parts that we're not sure about. But I think we can't just be anchored to the rigorous, analytical, provable methods, because I feel we're going to be missing out in designs and in opportunities to add functionalities to the mechanics. So I think both have to exist and to coexist and maybe supplement each other in a positive sense.
Jiga, go ahead.
Yeah, Chiara, wonderful talk once again. You touch upon many aspects. So you have such a diverse interest. It's hard to pin you down. You're interested in everything and has done a lot of things. There's one aspect you also mentioned. I want to discuss more with you. This is about problem-solving mode. Today, many questions are revolving around the more discovery, more inventive aspect. Problem-solving mode. Just one, there's a couple of concrete things. So ultimately, I want to ask you a question about giving a specific example you have, just a walk over to talk about it. But before that, I want to relate my own experiences so you see where I come from. So many people know we have in our group have been looking at hydrogels, right, for about 10 years. That wasn't my field, now it's become my only field, hydrogels. So I'm a man of hydrogels, very soft, everything. So, right, and many students are doing fantastically well. So then at some point, demonstrate some use. Of course, hydrogels have been used, but we heard you have done mechanics, and maybe mechanics can help hydrogels in use in some new useful ways. So I was very desperate. Give me one example. Our work can be used by common people, right? So reasonable thing to do. So then just by luck, I had a former student who had a company. And he is, you mentioned stent. His company is about stent. One particular thing about stent is you need to deploy stent with a guide wire. So this guide wire, of course, is stiff, flexible, everything we like about it is raw. So all stent wire need to be covered with hydrogel. It's no. The function of a hydrogel is just one, essentially, to make it slippery, to make guide wire slippery in the in the blood vessel. So now they're okay. This is a problem. We already published a paper about making coating, hydrogel coating on metal. We published a paper. Many people published a paper. The paper went on decades. But then you look at FDA literature, it's still a problem because these things fall off, goes into bloodstream, actually causes severe problem, not a trivial problem. So we have expertise, but when you begin to talk to companies and you see all these fancy talks, including our own work, it's just too fancy. So I won't go through the detail, the back and forth, but so my point really is when we talk about real people have a real problem, and then we recognize our fancy papers are just off target. So I want to hear your own experience when you are in problem-solving mode. You have something more advanced, but some of the advanced, maybe you already begin to talk to real people who have a real problem. Do you have an example you can relate to?
Jigang, I think your question and your comments a little bit echo what Catherine, brought up before. Is the question of, is it the science or is it the engineering, right? And I mean, in a way, it's a little bit I feel like it's a bit the curse of the academic culture today, right? Is that, you need to choose. If you want to solve a problem somebody else, hence make a stand better, a more reliable hydrogel that doesn't peel off your, nickel titanium wire. But then you kind of need to give up the fancy journals. You kind of, that's great. You should be proud of having solved somebody's problem, but then, then you solve the problem. then you're gonna get a pat on the shoulder from industry saying, thank you for solving my problem. Or you need to go for the fundamental science, the more kind of daring, creative, and imaginary idea that sometimes just end up being more like proof of concept demonstration of gizmos, right? Rather than something, but for some reason, for the way just the review system works and the publication system works, you can publish, much more visibly in higher impact journals or other avenues. And I think it's, again, it goes back to the answer I give to Catherine, is it goes back to what is it that motivates you to pursue certain scientific topics. And today, for me, there is a bit of both. I mean, I chose to speak about the more imaginative side for this seminar because I feel like it's maybe more broadly interesting to a wider, audience and more inspiring, I guess. But I think there is a lot of work that I do in my own lab that has to do with the temperature sensor. That piece of the work. It's hydrogels too, There's still polymers and there's still ionic conductors. But, those are somehow much more problem solving oriented. And in fact, we spend a lot more time prototyping things that actually work repeatedly for thousands of cycles, but then we don't write papers about them as much, right? It becomes a question of really, can I make this prototype work and can I test it? And we will write papers, right? But now it's been maybe 3-4 years of just mostly research, which has made enormous advances, but less of the type that would be publish or perish. So the question is the community, right? Is what do we value? Like, what do we want the young assistant professors to pursue? And how do we somehow attach a metric to those kind of advancements in mechanics, right? So that to say, hey, I solved a lot of industrial problems, but I published no papers, right? Is that something Harvard would like for tenure? I don't know. I mean, you tell me, right? I think we as a community, something we need to think about it and figure out a way to somehow attach a measurable success metric.
Sarah, on that point, maybe there is a third way. So we have a great role models. So John Rogers, for example, fancy papers plus practical things. And even older role models, George Whitesides, many companies issue fancy papers. And George actually wrote an article early, maybe 10, 20 years ago about doing highly visible research from not only push and pull, pull meaning technology, pull you into a particular set of problems. So there is a third way. I'm just having a conversation with you because you seem to have such a diverse interest, practical, useful, and also imaginatively creative, crazy, I mean to say, and creative. So you must thought about all these balances. So look at you, you are a third way, right? You're doing both. You're not picking and choose.
Yeah, I mean, I think it's, in a way, it's easy to do that once you are an established tenured professor at Caltech. You know, it's like, yeah, I can do it. What else? You know, what can go wrong? You know, worst case. I think it's just harder to do it if you're just starting up, or if you're a younger assistant professor defining your own career path, like Chimin was asking before. I think. You know, I think the examples of John Rogers is a great one, but that's I find it, let's say, hard to reproduce in the mechanics field, just because you need to strike this balance between you know, being attached to the fundamental mechanics community and the device community and the medical community and so on. It's something that I think takes many years. You know, it takes you know, a career to get to that point. And you have to have the right idea, the right example, the right application that somehow has the both aspects of being, you know, incredibly innovative, beautiful, and interesting from a fundamental standpoint. But that's, you know, there is an overlap of these Venn diagrams that's a narrow, it's a narrow spot. So again, the field of mechanics, maybe it cannot be necessarily concentrated in that narrow sweet spot of research. I think there is also the aspect of, look, there is a lot of fundamental work that's important for applications. The question we need to think about is, you know, if it's something that serves industry, why doesn't industry do it, right? Do we need academia to solve industry problems? And I think that's, again, it's a philosophical question, right? We need to think about where is the place of mechanics in the broader community in terms of balancing innovation with just applications-oriented problem solving.
I may have a comment. Zhigang, the examples that you gave, they are more related to the chemistry, biochemistry, material science. Another example, for example, that I can mention is Bob Langer from MIT, and is similar to the other two examples that you gave. And when you go to the mechanics arena, then I think we may have a different scenario that becomes the reality that may make this transition a little bit more difficult. Let's say, to have this impact in commercial applications, because at that level that we are talking about, then essentially you have to operate your research targeting an industry, for example, that would be very financially viable. What I mean is industries like medical field, for example, like why NIH has a much bigger funds than NSF, or chemistry, biochemistry, pharmaceuticals. Then those, I think they are quite different, although I think there is a lot of room for mechanics too. Because, for example, the initial question that you asked Chiara, right, in the beginning, also about the commercial applications. And one word that I can see that give us a focus and also a big challenge. For example, if all that Chiara does, for example, if we could scale it, it could be commercially viable. For example, if we can make it very small, okay? But then as we scale down, then it's a multifunctional system. When you change scales in space and in time, you don't expect to keep the physics the same. And then maybe we can have systems that could be applicable, like Chiara was talking about at the biological level, something that you would swallow, that at the end would be biodegradable, for example. Then, for example, scaling in space and time may offer an avenue, but that's just a thought.
Okay, Li Hua, do you have a question?
Hey, Chiara, wonderful talk. Yeah, my main question is about spatial temporal response of material. And maybe let's talk about your second example. So you build a relative complex structure, right? So to control, you have some components which control temporal response, but you also need like multiple layers so that by tuning the gap in between to control the spatial, so that you also have a distribution of different deformation in the space. So then, yeah, but you have to use a relative complex structure. My first question would be, so how did you manufacture this? Is that like, do you need a single material or multi-material? Or more generally, do you have a good general way to spatial and temporal control?
Yeah, hi, Leo. So I'm assuming you're referring to the second example being the
shape memory polymer.
The shape memory polymer, so the lotus leaf and the self-weaving structure. Yeah. So yeah, there is a piece I left out for brevity, which includes the fact that this particular system included shape memory polymers that are 3D printed with the usual Stratasys object printer with different thickness. So that gives the temporal control. But there is one element that I kind of left out in the story, which is in order to trigger the deformation, we also include pre-stress. So a lot of these, in this case, the pre-stress was applied by sandwiching between these, you remember the base, the brackets, and the bumpers, the three elements? This is done like a sandwich. So there are base and bumpers and brackets on top and bottom, and in the middle, we have a pre-stretched membrane. Why do we do that? Because that effectively incorporates in the structure a strain energy that is released once the materials, the shape memory polymers soften at higher temperature. So the bracket become softer, they begin to bend, and then the pre-stretch that comes from the membrane is what causes this uniform compression initially that then kind of allows for the complex morphing. So in this case, to answer your question, the system is 3D printed and then assembled. So there's two different materials. There is the shape memory polymer, that's just Vero White. It's a single material type. And then there is the membrane. However, in other work that I've done with some former students at ETH Zurich, we showed that with the proper 3D printing technology, for example, using laser 3D laser lithography, photolithography, like the nanoscribe, you can embed these pre-strains inside the 3D printed parts. So what I mean with that is that instead of having to assemble the structure and have the passive layer, the polymer, and then the pre-stretched member, what you can do is to simply add pre-strain in the 3D printing by, for example, over polymerizing in selected area of your structure. So imagine you have your system, and certain beams you can basically expose to the light beam or a light beam with higher intensity to cause higher cross polymerization. This includes a pre-strain, which eventually, when the element is released from the printing substrate, causes this differential warping or shape morphing. I think you can do both. You need to be clever in the 3D printing approaches. In the case of the Stratasys, we could not pre-embed pre-strains or pre-stresses as we were writing the parts because the software of the printer doesn't allow it, but other printing methods may. So you don't necessarily have to have too many materials. I think personally, I would prefer to have the lowest number of failure point, hence the lowest number of materials, and control the pre-strains and pre-stresses as you fabricate. But not all fabrication methods allow that.
Okay, next, Hussein, thank you for your patience. Go ahead. Hussein Aksoy. Do you have a question?
Yes. Do you hear me?
Yeah.
Yes.
Thank you very much, Professor Daraio. So I have two questions in your presentation. At one part, well, you showed us a simplified model. Basically, you try to simulate your problem by using simple elements. And we have been using two different definitions for approximately more than 100 years. So which is, one is the stress and the other strain. And we have been using much more complicated structures and trying to build the system from
Hussein, we cannot hear you clearly. Maybe if you don't mind, that you can turn off your video.
Sorry.
Sorry, I couldn't hear the question. It was really broken.
Okay, do you hear me now?
Yeah,
yeah, it's much better.
Okay, sorry. Now, we are building hierarchical structures, and now the problems that we have been dealing are getting more and more complicated. So this increases the computational cost, of course. So in order to solve our problems, we have been building definitions. One is the stress, and the other one is the strain. Stress as a measure of force and strain as a measure of deformation. And we link these two somehow with some mathematical expressions. Of course, there are different models. For example, we have different theories. One is the micromorphic theory, which combines the so basically you bring the effect of microstructure to the macroscopic level and you go down instead of modeling the whole structure. So do you think that such kind of material models can help us in designing such smart structures? And the other question is...
wait, hold on. Which material model did you say? I couldn't hear you.
For example, micromorphic material models.
Mm-hmm.
So we are using liquid crystalline elastomers, and so basically we are bringing up the microscopic properties to the macrostructure in order to have some material properties, in order to reach some material properties. We are designing the material now from the microstructure.
Mm-hmm.
So of course we have some problems due to the computational expense. This is a big issue. And you are trying to simplify such kind of things, of course, in order to avoid it. So do you think that such kind of theories can help? This is my first question. And the second question is, we have been using stress and strain as a measure of force and as a measure of deformation for more than 100 years. Of course, this simplifies our analysis because 100 years ago, there was no computer and people have been trying to reach some analytical solutions for some engineering problems. But now we have computers. And we have been using computational techniques approximately for more than 40 or 50 years. So do we need another definition for engineering purposes instead of stress and strain? What's your opinion on that?
Well, let me answer the first part of the question first. I think there is space for these hierarchical models. I think they may not be, for example, the models you were mentioning for liquid crystal elastomer, in which you look at the alignment of the molecules and then try to determine the final shape and the final mechanical response. And there is space because we need to understand, especially as newer and newer compounds, polymer structures, hydrogels, and other material systems are coming online and are 3D printable or fabricable in different ways, understanding their fundamental response, their deformation patterns, and their response to external stimuli, it's essential. It's additional data we need to account for when incorporating them in this robotic matter or these architected systems with multiple functionalities. So there is absolute interest and necessity for this type of model. I don't know if they are going to be the best path forward for design, because like you said, they're computationally expensive. And when you want to design a full soft robot from the ground up, these kind of approaches are just simply too inefficient to get to the final architecture at the macro scale. So I think there is space, but there is space limited to what you're trying to understand in the specific case of the material per se. I didn't understand the second question. Like, what do you mean get away without stresses and strain? What do you have in mind in terms of alternative parameters? I mean, I think they've survived over 100 years because they served us well, right? So they allow us to understand the formation and response of materials in a quite important and accurate way. So what did you have in mind in terms of getting away of stresses and strains?
Well, okay. So basically at atomistic structure, or from fundamental point of view, we build up everything from particles, and we generally look at the forces between the particles, right? Yeah. And particle force. And when we continue, when we go up to the macroscopic scale, then we have the continuum, and then we begin to use the stress and strain.
Yeah.
And in fact, there is a model called peridynamics. Instead of using a stress term in the classical momentum equation, they use some integral equation which depends on the displacements. It's an analytical theory. And so the basic idea of this theory is to use the same type of equation at all length scales, beginning from the atomistic level to the continuum level. So this is basically my question. People have been using it. This theory is devised by Dr. Silling from Sandia, I think. So this is what I'm asking. I mean, do you think that could it help, or shall we need some other thing?
I mean, I can tell you that based on my own experience, and again, bear with me, we are experimentalists here. So I would say for now, what I've seen in terms of reasoning pragmatically, in terms of designing these complex architectural materials which respond to stimuli, I mean, to a certain extent, stresses and strains suffice. I mean, they work fine in terms of expectations of response, at least averaged over certain mesostructures. And maybe that in the future a more general theory can help. that's not. I'm not too familiar with what you're thinking, so I can't comment really in depth. Certainly, I think what we need to do is to think of ways to be more efficient in design. When I mean efficient, I mean computationally less expensive ways to describe deformations. And if that comes with a more universal theory of displacement, great. We'll have to see how things evolve.
Thank you. Thank you very much.
Baoxing, do you have a question to ask?
I'm you.
Yeah, thank you for your patience.
Thank you so much. I just after listening this talk left for a while, so I try to catch up what the question had already been covered. So first of all, thank you so much for the great talk, very inspiring from fundamental to applications. So I have two quick questions. I don't know whether you have already previously covered to reply to others. The first one, very quick. In the first, the part, you give the plot, say you have a T-shape or just the bar to give a trend. I think there is a plot to say this is a Young's modulus or Poisson's ratio. So when you grow to from 2D to 3D, very complex structures, so you still can predict in theory what's the specific say the Young's modulus or Poisson's ratio. Not the computation. Just a general theory. Can you still predict if you have a different combination of a T-shape or one shape, even if from 2D to 3D? I don't know. First of all, I don't know whether you have already replied this question.
No, I did not. And this is it's a really beautiful question. It's something we're working on. I think this idea of interpreting and in a way learning how different geometrical components, how different, say, elements and connectivity and availability of this type of connections improve the fundamental understanding on materials microstructure and its relation to property. It's very exciting to me, because I think right now a lot of the work I've been doing and I've seen in the literature is linked to, hey, if I have this geometry, look at the beautiful property I found. But I think we need to do more in terms of understanding, well, why is it that we see this beautiful property? You know, some things we understand, like the bow type shape that gives negative Poisson's ratio. So there are some things that seem to appear more regularly in the literature of architected materials that tell us if certain structure exists, then I expect this property. But we don't have a systematic understanding of all of these nuisances of, well, what if I have a T shape? What about the cross shape? What about the bend shape? What about the curve? And how each one of these elements in a certain frequency of occurrence is going to lead to specific mechanical properties. We just don't. We have been, as a community, looking at very similar geometries, right? You know, the lattices are kind of similar. The one we see, like Kelvin, octet, and diamond lattice and cubic lattice, they're kind of all variations of the same symmetries to a certain extent. And I think, to me, that's as limited the space of material properties. And I've only showed Poisson's ratio and Young's modulus as an example, but you know, these diagrams that with the dots that you saw there really are multidimensional, right? We can think about strength, you can think about shear moduli, you can think about wave speed, you can think about, you know, fracture toughness or yield, and all these things. I think it's something that we could in a way design independently for. I think, though, we don't have yet a good grasp of what leads to what. And I think this beautiful tool that Chris is developing is giving us the capability to at least understand what are the key elements that lead to these different directions, right? How do I get more strength, or how do I get the better shear modulus? We have maybe a vague intuition right now to say, well, if I have a slanted element, you know, probably the shear is going to be lower. But I think we can do more in terms of understanding the structure to function relationships. And in terms of your question, yes, we can do the same type of exploration in 3D. Mm-hmm. It's work in progress. The truth is that, I mean, this is something Chris has been is working on as we speak. So it hasn't reached a complete maturity, but I think that's where this work is leading, is the question of I can let materials grow, but if I provide different resources, so for example, if I tell the material you can grow, you can have this cellular automata that propagates, but you only have straight bars, you probably are going to end up having a layered composite. But then you say, well, now I give you also round particles, you're going to have a composite material with a different microstructure. And depending on the availability of resources and the rules you encode in the generator, you grow different systems. My hope is twofold. One thing is that we can expand the parameter space of mechanical properties we see. So, reach extremes that we haven't yet been able to tap into these Ashby plots that, for example, Professor Fleck has been, presenting in his own talk before. So that's one thing. And the second thing is that as we expand this property space, we also learn what are the fundamental building blocks that enable certain properties beyond the ones that we can intuitively guess. And some of them are going to be the one you intuitively guess, but there are new ones that you're thinking, oh, I didn't realize that this type of, for example, zigzag geometry is going to lead to this property. And I think the structure to function relation is something that I've always found intriguing.
I see. I look forward to that. If we can know in theory, predict that we can control the growth direction, just like the tree root, we can just grow 3-dimensional or 2-dimensional, or if you can replace a part of the T-shape, we use electrical, the Zhigang's, the soft gel, the conductive, the material says I only the electrical conductive along the specific way, but the others not. Then you can control all the things together. You have the mechanical theory to guide the growth. I think that would be fantastic.
Yeah, I agree. I'm really excited to see where this goes.
So the second quick question. Sorry about that. So the second question in the second part, you show there's from the flat shape to the 3-dimensional shape, no matter it's a waved structure, you show the video. I don't think whether it is possible, probably you didn't show that when you from the flat to the part of in a middle shape, not to the final interwave structure, whether it can be stable or can stop for here, or any stage can be say stopped by your design or by your external stimulate.
Yeah, so the video right now basically runs to the end because we just let it evolve until the bumpers come into contact. So right now, what stops the deformation is the fact that all of this bumper element come into contact and effectively lock the shape to the curved position, either the interwoven structure or the leaves, and we've done a few other demonstrations. However, I think it's all related to this diffusion mechanism triggered by temperature. Basically, there's a softening of these brackets that enable the deformation. I think if you could freeze it, as in, suddenly bring the temperature to a lower point, from basically to the lower starting point, where you say, okay, I don't want you to continue soften and deform. I want you to stop in between. For example, you quench it very rapidly, assuming you don't break it in the process, you can stop the deformation. I think there is an interplay between this pre-stretch that brings the deformation to occur and the softening of the brackets that allow, basically, they act like springs and they allow certain part to deform before other parts. But the moment you make this bracket stiff again, in this case by lowering the temperature, I would expect you would be able to stop it in between. We haven't tried it.
I see. Imagine you have a flower that's 1 day flat, then second day a little bit folded, just 1 week lasts long, then that would be fantastic, amazing.
I think if that's the functionality you want, it can be programmed into it. This would not be hard. I think having intermediate steps, I do think that's something would be a relatively straightforward additional function you can program into it.
I see. Thank you so much. I finished my question. Thank you.
Great. Yeah. Changyong, do you have a question to ask?
Okay, thank you, Tom. Let me ask a question. I have listened to your discussions. It's a very insightful discussions. Thank you so much, Chiara, for the fantastic talk. You know, nice to see you again. So, Andy, I think the growing material is a very interesting topic. Here, I want to ask a question. When you do the fabrication, so when you do the growing, the sequence, you know, they have a sequence to be able to grow from starting, you know, a small parts grow bigger. And if you do the fabrication, you have to follow the same sequence to for using the 3D printing to do the same, or it can be, you know, a random you know, printing part generated.
No, I think, so there's two aspects to that. I think if you just want to reproduce the final geometry, you can just basically convert the final shape in 2D or 3D of these sheets or 3D objects I showed into STL file and just print it. I think once the geometry has been generated and evaluated, for example, via FEM or other computational method of choice, then you can just print it however you like and use different types of printers as long as the materials basically that are constitutive materials for the printer are linear elastic. I expect the response to work as predicted. So that's, in short, that's just a mean, the growing metamaterials just a mean to design and to generate geometries of these building blocks that are not the standard shapes of truss-like lattices and so on that you find in the literature. So that's the first thing. The second thing is a question of, you know, that we've been thinking about, but then, you know, with the shutdown, we haven't done much experiments on the matter, is to see if we can really self-assemble things, right? It's like once you have these rules and the materials can design themselves in a computer, can you do that also in the lab by providing, for example, a certain number of building blocks and letting them assemble themselves? And that's a question remains open. I mean, I think in principle you could use self-assembly at providing limited number of resources and building blocks and, you know, like making them fall into place. But we haven't shown that yet. I think it was one of these things that we were dreaming of doing, and then the lab shut down, and then we got stuck working on computers.
Okay. Then thank you. Then let me ask a follow-up question. For your second part for the soft robotics, for the programmable materials. So now it seems many people, you know, attack the programmable, you know, the responsible materials is a low responsive speed. You know, I think either the chip memory polymers or the hardwares, you know, their response speed is pretty low. So what's your vision, you know, in this aspect to improve and to get it first the response? And definitely, you know, Xuanhe Zhao, professor, so he recently did a lot of the magnetic response material can be quick, but you know, for other side, for other stimuli, for the thermal, for the, you know, for the light, all these kind, how can make it a response faster?
Yeah, I mean, I think it's again going back to the question of what problem are we solving, right? Why do you need a faster response? And then the question is how fast. I think if you, one direction that was discussed before is that you can miniaturize it. So if you make things smaller, if you make beams thinner, you know, even your diffusion limited problems and the, you know, temperature, pH, and so on, you know, of course, are going to be at lower time scales. They have less materials to percolate through and to diffuse through. I think so miniaturization is one way of doing it. The other way is to you know, go all together with different stimuli. I think light, for example, it's true. I mean, in some cases it's not very fast, but you know, it can get pretty fast for flagellas, for example, getting to relatively high frequencies. That this was literature I've seen from a couple of years ago, and hence you can get to timescales that are not you know, order of a minute, but you can get, you know, order of milliseconds. So So the speed to me is going to be inherent of what spin do you need, what frequency, for example, of clock operation do you need, and for what purpose. And then we can see if in this palette that I mentioned of materials that are available, of choices that are being constantly developed in terms of new reactive polymers and so on, we can find the one that can respond to our needs. It's hard to guess it without having a specific target, right? And to say, you need to tell me what the problem is, and then we can explore together ways to reach that. That's, for example, actuation speed or cyclic repetition rates and so on. I mean, you're always going to be partially limited if you're going to be using polymers. I don't ever expect to be able to get to gigahertz frequency of actuation just by the nature of the viscosity and mechanics of the problem. But I think it's certainly there is space for controlling these that we haven't necessarily explored for the proof of concepts because we didn't need to. But if there are specific applications to be addressed, then I think there is space to do something better.
Okay, thank you.
Did you have applications in mind where the speed of actuation is relevant?
I think for the, like hardware, like the chip memory polymers, and for the drug delivery related, they definitely is workable. But if we consider using some robotics, we want it can be more faster, definitely as fast as possible. And then it has troubles, is right? And yeah, but your insight for comments is I think is good. How to make it smaller and how to make it use less materials can be, in short range can get more energy to actuate. That's very good point. Yes, thank you. Thank you.
Believe it or not, this webinar, EML webinar, has been live for more than 200 minutes. Thank you very much, Chiara, for a wonderful webinar. And we'll keep you busy for a few more days. Looking forward to receiving your submission of the EML webinar overview. And I would like to thank all our panelists for another round of lively discussion, and those of you who joined us live today. Let's give everyone a big round of virtual applause.
Thank you.
Coming up.
Thank you for moderating this. This has been a fantastic discussion.
Great, yeah.
For great talk.
Okay. Coming up next Wednesday, EML webinar present Professor Stephanie Lacour from EPFL. She will talk about the soft neuron interfaces. A discussion leader will be Professor Sigurd Wagner from Princeton University. And I hope to see all of you next Wednesday, the same time. And before that, I invite all of you to watch the recordings of the previous EML webinars in YouTube channels and in Weibo, including this one, which will be available later today, and download the existing 5 EML webinar overview papers online. And thank you, and have a wonderful day or a good night. Bye.
Bye, everybody.
Chiara, you just broke the record of time. You're amazing.
No, thanks, Jigang. This was a wonderful opportunity. It's I think it was a good idea you guys had. I love them. I unfortunately watched them mostly offline because at 6 in the morning is too hard with kids at home. But I've enjoyed every one of these seminars. It was a great idea.
Yeah, it was actually intended. So I was thinking, if you, let's say you watch CNN or any late night show, the live audience will always be small portion compared to replay over the lifetime, right?
Yeah.
So we target this way. So our sense is that if you have several hundred live audience, the quality of a question today, you actually attract a quite large number of good colleagues, experienced colleagues to be here. So then that maintains the quality. You don't need to have a lot of people to be live.
Right.
But a long range, if any talk or any video is well produced, it will attract a lot of people.
Yeah, and you know, now my kids are gonna be so proud. I can tell them that I'm a YouTuber. So.
There will be more than thousands of views upcoming with previous EML webinar videos available online. It's accumulating all the time. Yeah. Thank you.
Thank you, guys. It's great.
So you will submit an overview, right?
Yes. I need to write it up. Just bear with me. The COVID has slowed me down a little bit, but didn't stop me. So I will submit the overview.
Yeah, it has been popular among people. People still like to read a little bit, especially the cited literature.
Yeah, and it remains there. It's going to be more stationary for the community to find. So I'm absolutely happy to do that.
Yeah. All right. Great.
Great. Thank you.
Turn, you're terrific.
Thank you.
I appreciate it.
Okay.
Bye.
Bye, everybody.